Good morning, everyone. It's the, oh, actually, you know what? I need to, hold on a second, guys. You know, someone made me realize I may not have posted the most previous Zoom session. Hold on a second, guys. There's something that I did not do, 622. I am just gonna cut this and drag it to the next Zoom here. Paste. Okay, now that's a moving. Good, we won't run out of disk space. Sorry about that. Good morning, everyone. Welcome back to the class. I'm recording. It's nice to see you all wide and awake and ready to do some homework. Today's homework is going to be homework number 8. We'll be doing chapter 9, which is on planetary geology. Our lab today, which I just posted, is lab number 10 on the landscapes of Mars, and that's a great, fun lab. Any questions? Good morning, Megan. Are you awake?
No.
Okay. Well, I wasn't until recently either. So during the course of today's office hours, you may see me run away to grab some much needed coffee. Okay, why don't we get right into it because time's ticking. What's our first problem? Chapter 948. Who wants to look at the numbers and read that for me? A couple of word problems today that'll take some time. Talk to me, people. Don't make me do everything for you, okay? You can at least read the question. That's not too much to ask.
Miniature Mars. Suppose Mars had turned out to be significantly smaller than its current size, say the size of our moon. How would this have affected the number of geological features due to each of the 4 major geological processes? Do you think Mars would be a better or worse candidate for harboring existential life? Summarize your answer in 2 or 3 paragraphs.
Okay, at the stage of development that we're at, we're roughly halfway through our planetary terrestrial geology lecture. And we have learned some things about the role that planetary size has.
Hey, Professor?
Yeah.
You're just like in a small box on the upper right of my screen for some reason. It's never happened before. And then it just says like the Zoom in the background.
Okay.
So I have no idea what happened.
You have miniaturized me.
Yeah.
Click on that box, and there's a little, how do I do this? If you click on that box.
Yeah, now you're on the left side, yeah.
There should be a little green button to full screen me. Then you want to go to speaker view, and then speaker view is in the upper right corner. You toggle between the Hollywood square tiles and the single person view. And then you want to lock speaker view by double clicking on my face.
All right, so it showed up with like settings or something.
Okay, wait, you got to describe to me better what's going on, Dennis. I can help
so
you.
what's going on is there's like a full screen as like a general, a video, an audio, a share screen, a virtual background recording.
Yeah. But are you seeing all the students in the class, or are you?
No, I'm not. I'm only seeing you right now.
And I'm in a little tiny box in one place on the screen.
Yeah, you're in
all
a
right,
small
okay,
box,
just
and
slow your roll.
I'm right. Oh, now you're right. It's just you now. Yep.
Okay, you fixed it?
Yep, just you.
Wonderful.
Perfect.
Okay, everyone, let's talk about mini Mars being, what would happen if Mars had been the size of the moon? So let's go to my share screen for a second, and let me show you guys the Mars topographical map that I just had up, that I just put onto your screen here today. For Lab 10, which we're going to do later today, you have a Landscapes of Mars handout, and you also have a Mars topographical map. And while this does not show you the actual color of Mars, because the surface of Mars, of course, is red, it does show you a number of interesting features. Can I zoom in on this? Yeah. A number of very interesting features if you look around the surface of Mars. Around the surface of Mars, we see a variety of interesting geological developments. Here, in the Tharsis Montes plains, you can see a number of massive volcanoes, which are actually taller than the volcanoes on Earth, if you can believe that. Mars also has oversized canyons, such as this guy here. This massive canyon is called the Valles Marineris. It's a massive version of the Grand Canyon, 7 times deeper and 14 times longer than our own Grand Canyon. So it's a massive chasm across the surface of Mars. And Mars also features, I don't know, some things that look like this. What does this stuff remind you guys of here? What are we looking at? Can anyone say anything intelligent about the thing that I just circled here? Or I'll even take something that's not intelligent. I'll honestly just go for anything that you have to think about it. Like, I'm asking, what is this stuff? What does this look like to you?
Maybe something like rivers or like erosion or something. Just
Yeah,
wild.
these certainly look erosional in nature. Very good. This looked like dried up riverbeds. They've even color coded them in such a way. They're color coding them by elevation. So the blue areas are lower elevation and the redder areas are higher elevation. So if these are rivers, then what about the Chrissy Planitia here? What would that make this?
Like a lake or ocean.
Yeah. Damn, Mars has got some cool features on it. It was once a very interesting planet. Of course, it also has some parts of it that look like this. What does this stuff remind you of? What do you think about all this stuff? Does this remind you of Earth? What's my point? I've got a point, but what is it? Does this remind you of Earth?
Would it be no?
Okay, well, what might it resemble then?
Kind of, would it be volcanic type things or
Well,
or
if you look
more
near the volcanoes, Dennis.
or warmer temperature or something like that?
No, that's not the right idea. Let's just address the volcano thing for a second. Maybe I can help. If you look near these massive pitted volcanoes, you'll notice, Dennis, that the surrounding plains are actually quite smooth.
Yeah.
Why might the terrain around volcanoes be smooth?
From like after the eruption, kind of like smoothing it out, like erosion type thing.
Very good, but it's not erosion. We would classify this on the 4 geological process spectrum. Do you guys remember what the 4 geological processes are? Let's start there. That would actually
Plate tectonics was one of them, right?
Right. So we have to include these in our answer. There's
Erosion, plate tectonics, impact cratering, and volcanism.
very good. So here are the 4. Sorry. Here are the 4 top. We have to address. Sorry. We have to address all 4 of these topics in our answers, the 4 geological processes. So I understand why you mentioned erosion, because erosion tends to transform the surface of a planet, but so does volcanism. Volcanism tends to make these smooth plains as the lava cools. So in other words, Dennis, I wouldn't think of this as being volcanic. Of the four geological processes, which one is represented here?
Would it be?
Come on,
Would
you
it-
guys can do this.
Would it be impact cratering?
Of course, these are all impact craters. So when you see a huge swath of Mars's surface covered in impact craters, which terrestrial planet does this most resemble? And don't say Earth, because Earth doesn't have anything like this. Come on, you can do it. Play the thinking game with me. Which terrestrial planet does this resemble?
The moon.
Yes, of course. This looks like the surface of the moon. I also would have accepted Mercury because Mercury's surface looks like this as well. Both of those worlds are significantly smaller than Mars. Okay, so what's that mean? Let me show you something else I think is interesting while you're trying to think your way through this. I have a slideshow that shows a sort of single monochromatic elevation of Earth, Venus, and Mars. I'd like to show that to you. This is what the surface of Venus looks like if you subtract out the color and the clouds. This is obviously the surface of Earth. And this is Mars. You seeing this, Tess? How does Mars differ from the other two? It's got something to do with our most recent discussion. What do you think?
Can you just kind of restate like your whole question?
Yeah, I guess I'm
Okay.
being a little vague. There's something different about Mars. The surface of Mars looks different than both the surface. Venus's and Earth's surfaces are obviously different,
Yeah.
but Mars is different than the other two in a unique way. What does this picture have that these two pictures does not?
Hold on. So this picture from the other picture you just clicked on?
Yeah, this is Mars,
Yeah.
this is Earth, and this is Venus.
Would it be the little, I don't know, those volcanoes or something like that?
These are volcanoes, yes, but Earth also has volcanoes, does it not?
Yeah, it does. Yeah.
So that's not something that's different than Earth. It turns out that Venus is dotted with volcanoes as well. So we're going to have to try again, because if you look here, we can see volcanoes in Hawaii. They're not as big as Mars, but there are volcanoes here. There are volcanoes all along the Pacific Rim of Fire. There's lots of volcanoes here. On Venus, you can see the volcanoes a little better. They're just not as tall as Mars's volcanoes. Volcano, volcano, volcanoes, you know? So we can see volcanoes on Venus too, although they were smaller. So I understand they don't pop out as much. But Dennis, there's something else besides Mars. There's something else besides volcanoes that Mars has a lot of that the other two planets do not. And it's not like a subtle thing. It's a hit you over the head kind of thing. But I want you to say it. I don't want to say it. Do you understand what I'm talking about, Tess?
Not really.
Shit. Haven't you ever played the game? Which picture is different than the other two?
Is it one of the 4 geological
Yes,
things?
absolutely
So
it is.
would it be impact cratering?
Yes, of course. I
Alright,
wasn't thinking that was going to be a hard question. I was thinking,
yeah.
holy shit, look at all the craters all over the surface of Mars. Look at all that. Do you see anything like that on Venus and Earth? So why? Why does Mars have craters all over its surface? And yet Venus and Earth are comparatively crater-free. That might be a harder question. Did all the impact craters just hit Mars and they missed Earth and Venus?
I don't know the answer to that.
Well, I guess that's because we didn't really talk about the function of impact craters. Impact craters tend to be present on every world. I mean, look. If you have the Earth and the moon is covered in impact craters. The Earth is not. Does that suggest that all the impact craters happen to hit the moon, which is significantly smaller than the Earth? Do they all miss the Earth? Oh, look at that little guy. He's a little tyke, isn't it, Michaela? What a cutie. Is that her? What's her name?
Yeah, her name's Peyton.
Peyton?
Peyton, yep.
Well, she is a cutie. Hello. Hopefully maybe she can answer my question. Peyton, why did all the meteorites strike the moon and miss the Earth? Does Peyton have an answer to that question?
I don't know. She just likes the movement, I think. That's why she's looking at the screen.
Okay. Well, we'll keep her entertained, if not you guys. All right.
Would it happen to be something that has to do with like a gravitational pull towards the moon? Like,
that's a good idea, Tess, but wouldn't the gravity of Earth be stronger? If that were the case, wouldn't Earth pull all the meteorites to it and not the moon? Kind of weird that they would strike the smaller thing. I don't think it's gravity, because if it was gravity, we'd see more here than there.
or is it just because the moon is smaller, so we see more of the like hits and whatnot, opposed to Earth, where it would be more spread out because it's larger?
I don't think that's an idea too, and it's not a crazy one. But the thing is, Mars is smaller. Oh, okay, right. So, no, Mars is bigger than the moon, but you can still see the craters all over Mars's surface. So if it's about the density of craters, right? Like the moon is 100% covered in craters. Mars is like 50% covered in craters. Earth and Venus are like 0% covered in craters. But the number of rocks flying through the solar system should be consistent and random. It's not like the rocks can steer themselves as they fly around the sun. They're going to strike, in theory, the planets with equal intensity. And if you have more surface area, you have more target area. The secret is to understand where we see craters on Mars. Like, look over here near the volcanoes. there are clearly fewer craters. And I was thinking there was a simple, easy explanation for why. Why don't I see any craters over here? Or why do I see relatively few craters?
Maybe because the volcanoes filled it in.
That's right, Michaela. So perhaps at one point, all these lower level yellow areas covered all of this, and there were craters everywhere. And then these volcanoes erupted, and their lava paved them over. Maybe there were once craters here, where the Valles Marineris is, and then it ripped a hole through this plain. Maybe there were once craters over here, where all these river valleys were, and then they got washed away into an ocean. Maybe other types of geology erase craters. Now, in our last lecture, we learned about lithospheres. What's the lithosphere? What's that all about? Do you guys remember what the definition of a lithosphere is? Why don't you regurgitate it from your notes? What do you think? Could someone read that definition for me? Just read the definition of lithosphere from your notes. Megan, do you want to do that for us?
I'm trying to find it. I don't remember what it was under.
Under the 2 ways to layer Earth.
I have 2 methods of layering Earth. Lithosphere equals hard, frozen, brittle outer layer.
It's the hard, frozen, brittle outer layer, right?
Mm-hmm.
The brittle outer layer. So so the lithospheres are, oops, sorry. Lithospheres measure the heat of the interior planets. You'll notice that the moon's lithosphere goes all the way down to its core, meaning it's all frozen all the way to the center. Mars is frozen to about halfway, and Earth and Venus are only frozen a little bit at the outside. So on these planets, we see lots of volcanism, erosion, and tectonics. On Mars, we see a little bit of past volcanism and tectonics. On the moon, we see very little volcanism, tectonics, and certainly no erosion. If Mars was the size of the moon, I suppose it would have had more time to cool off. And a lot of that internal heat that was stored inside the planet would have dissipated out through the surface. And there would be no more, you can't have volcanoes unless you can crack through this lithosphere, nor can you have plate tectonics And without volcanoes and plate tectonics, you end up not having a lot of erosion because you kind of need an atmosphere for erosion. And the smaller planets don't have atmospheres because they don't have any volcanoes. There's a connection between the two. There's still a lot of puzzle pieces you guys haven't gotten yet. So why don't I try to write it down for you and you can just follow along at this point. If Mars had been smaller, say the size of the moon, we would expect to find many fewer of the interesting types of geology we see on its surface today. A mini Mars would have lost its internal heat much faster, resulting in a thicker lithosphere. A thick lithosphere will not allow the development of geological processes like volcanism or plate tectonics. This means no more large volcanoes or deep canyons. The lack of volcanism would mean little to no atmospheric gas. Actually, let's put a comma there. The lack of volcanism would mean little to no atmospheric gas. Class, I need to erase the top lines up here. So I'm going to erase like the first 1, 2, 3, 4, 5 lines. If you have an objection to that, you better tell me right now. The lack of volcanism would mean little to no atmospheric gas, which would prevent erosion due to wind and water. The only geology we would expect to find is impact cratering. Which would blanket the surface. You guys keeping up with me? I'm going to erase 2 more lines.
Can you move the screen up a tiny bit? No, just so right after where it says geological processes like volcanism and plate tectonics, so the lack of volcanism would mean little to no. Yeah, right there.
Okay, so you actually meant move the screen down.
Yeah, that's what I meant. Yeah.
Okay.
Yeah.
Now they asked us to comment on life, so let's summarize with a final sentence. I'll erase these guys. In short, a mini Mars would resemble the moon. And thus be a unlikely place to find life. I'm just going to give you guys a moment or two to try to catch up to me. Let's see here. Everyone, I might decide to change the next homework question because I think the next one I asked was about Venus, and that's going to be a complicated one for us to tackle until you've gotten the rest of my lecture on planetary science. I should probably make a small adjustment for our sanity. Oh no, okay, 55. 57. Oh, that must be in the next one. Okay, no, that's cool. Oh, wonderful. Never mind. I was getting 2 different homework assignments confused. That's excellent. Okay, do you guys have all that? Does anyone need more time? Sounds like everyone's good. I'm erasing. Okay, next up, someone read me the problem. 55. Tess, you want to do it?
Okay. Surface area to volume ratio is the title. And it's compare the surface area to the volume ratio of A, the moon and Mars, and B, Earth and Venus. In each case, use your answer to discuss difference in the internal heat of the two worlds.
All right. I have kind of a weirder concept here than, instead of using the typical planetary science comparison of surface area to volume ratio, I think it's a little nicer for planets to use the volume to surface area ratio. The idea being that if you have a planet that is a sphere, whoa, was that from me or was that from you? Was that my sound or was that your sound?
I think it was.
Was that me? That was loud as hell. I think, okay. I need to get rid of this. Get rid of that too. I think that was my email, sorry. Typically planets are spherical and they have a radius r, and spheres have volumes equal to 4/3 pi r cubed, and they have a surface area equal to 4 pi r squared. In some sense, the amount of heat a planet can hold will depend upon its internal volume. So the amount of heat that a planet can hold depends upon the quantity or the amount of volume it has. But remember that planets lose heat by shining away infrared radiation into space. So this is infrared radiation leaving our planet. The more surface area you have, the more infrared light you can shine into space, and the cooler your planet will become. So whereas the volume is kind of like a measure of the internal heat of a planet, the surface area is a measurement of the amount of cooling a planet can proceed with. More surface area means more shining into space. If you take the ratio of these two, you get something that looks like this. The volume over the surface area. If you divide these two, you can cancel out the 4s and the pi's, and you can cancel out 2 of the radii, and you get 1/3 times the radius. And the volume to surface area ratio is sort of proportional to the amount of internal heat that a planet can hold. Actually, it's the ratio of the internal heat to the cooling. But the bigger that number is, the more internal heat your planet can hold. So let's try to compare, I'm sorry, what was the part A again, Tess?
It was the moon and Mars.
Okay. I happen to know their radii already, so let's set this up. We're going to do the volume to surface area ratio of Mars, and we're going to divide it by the volume to surface area ratio for the moon. That will give us 1/3 the radius of Mars divided by 1/3 the radius of the moon. You'll notice that the 1/3s cancel out. Now, the radius of Mars is 3,400 kilometers, and the radius of the moon is 1,700 kilometers. What does that ratio equal? Divide them up.
It equals 2.
And what's the meaning of 2? Megan?
The heat.
Okay, keep going. Two
No.
heat units? What do you mean? No,
Oh, at 2 degrees.
not 2 degrees.
Um,
Ratios tell you how many times.
oh, 2 times would be 2 times hotter.
Something like that. 2 times more internal heat, or 2 times the heat holding capacity. Mars holds twice the internal heat of the moon. How about part B? When you're ready, Tess.
Part B is Earth and Venus.
All right, so let's set it up exactly the same. In part B, we'll take the surface area to volume of Earth divided by the surface area to volume of Venus. So we have the radius of Earth divided by the radius of Venus, 6,400 kilometers for Earth, and Venus is 6,050 kilometers. What's that ratio give us? What you got? Quickly now. Anyone? Ian, what'd you get?
Uh, 1.05.
How about just 1? What's that mean, Ian?
It's 1 times hotter.
Well, 1 times hotter. Is there a simpler way to put that than 1
It's
times?
hotter.
Is it though?
Not really, but a little bit.
I mean, look. Well, where's the little bit come from? The 0.05?
Well, I'm assuming from the 1, if it's just a little
Look.
bit hotter.
I think you're missing something, Ian. Ian, if I have $50 and you have $50 and we take the ratios of our $50, you get 1. Does that mean I have 1 times as much money as you?
No.
I mean, kind of. But it doesn't mean I have 1 times more money than you, right?
Mm-hmm. So they're just the same.
That's my point. They're the freaking same. That's what a ratio of 1 means. There's no one is greater than the other. Earth and Venus Earth and Venus hold roughly the same amount of internal heat. I think I've killed these markers. Okay, I want to erase. Are we good? Sorry, I want to get some of the ink off this board before I bust out a new marker. All right. Okay. Megan, why don't you read us the next question? We'll let
Okay.
Michaela off the hook a little bit since she's babysitting. This is chapter 9, number 57.
It's lunar footprints. Assume
Okay.
that the moon is hit by about 25 million micrometeorite impacts each day. This number comes from observations of meteors in Earth's atmosphere, and that these impacts strike randomly around the moon's surface. Also assume that it takes about 20 such impacts to destroy a footprint. About how long would it take for one of the footprints left by the Apollo astronauts to be erased? And they give us a hint, and it says, use the moon's surface area to determine the impact rate per square centimeter and estimate the size of a footprint.
All right. This is about a very famous photo from the history of planetary science. And if we go to, I don't know, slide 90 or something, the moon is struck every day by not only large meteorites, but tiny little pea-sized grains of sand. And because the moon has no atmosphere, even the small microscopic sized grains of sand and very small meteorites that would normally burn up in Earth's atmosphere make it down to the surface and create little mini craters on the moon. Now, when the astronauts landed on the moon, they discovered that the surface of the moon was covered in a fine powdery soil, which is known as the lunar regolith. Here's a picture of one of the lunar rovers, and you can see the moon. It's basically moon dust, and you can see moon dust being kicked up by the tires of your lunar rover. Why is the moon's surface covered in moon dust or the lunar regolith? It's here you can see the footprints of the astronauts in the regolith. It's because every little micrometeorite which strikes the surface of the moon is going to leave a small impact crater. And if you fast forward over billions of years, you'll eventually grind the surface of your planet up into silicate dust. Now, this is a picture of Neil Armstrong's boot print in the moon. And if this boot print had been made in the mud in your backyard, you'd expect this footprint to last maybe a day or two at best, or at least until the next rainstorm. Rain and wind would very quickly deteriorate this boot on Earth so that it would get washed away and disappear from the surface of Earth. But on the moon, there's no atmosphere. You're basically just touching the vacuum of space. And that means there's never a gust of wind or never a drop of rain on the moon, which will be able to disturb this. What would possibly cause this to be disturbed? The only answer is more micrometeorites raining down on the surface. That means this boot print is going to be around for a lot longer than a boot print on Earth. The moon lacks erosion, and erosion is a powerful force for transforming the surface of a planet. Let's make a little probability argument together. We're going to do it slightly differently than the book suggests. I'm going to walk you through this. So here's the moon. The moon has a radius of 1,700 kilometers. And here is Neil Armstrong's boot print on the moon. And each day, micrometeorites are raining down on the surface, kind of like darts being thrown at a dartboard. The meteorites will be striking the moon in random locations, but we know that they're being hit with a rate of 25 million per day. Sooner or later, one of these impacts is going to land on our boot. Our goal is to calculate first the probability that a single impact will strike the boot, and then to see if we can figure out how long it will take for 20 of them to hit the boot. Class, what if Neil Armstrong's boot had been so big that it covered a quarter of the moon's surface? What would be the probability of a single micrometeorite striking the boot? Can you tell me the answer to that question? If the boot print had been this big, what would be the probability of the boot getting hit by one impact?
25%.
Very good, Dennis. And Dennis, you reasoned, I think, that this is a quarter of the surface of the moon, so 1 in every 4 would strike the boot, right?
Yep.
What you were saying then is that the probability is the area of the boot divided by the area of the moon. Now, the area of the moon is 4 pi r squared. From our previous problem, that's the surface area of a planet. The area of a boot is its length times its width, if you assume that your boot is like a square boot, which is, I don't know, a close approximation. Let's see if we can measure the area of my boot by comparison. I'll turn on my Wi-Fi. Let's see if I can get lucky here today with the screen share. I'll go to my screen mirroring and then I'll activate it. Let's see if something comes up here. Okay, cool. Okay, so you're gonna help me, Dennis, measure the area of my boot, okay? All right. I got a meter stick here. We're working in, what units are these again? So here's my boot. Dennis, how long would you say it is? Approximately. Oh, I guess I should try to get my toe right up to the line here. What would you say? Can you read that? Can you see my boot here? How long is it?
I'm muted. 30 inches.
Is that inches? Those are centimeters, pal. We don't work in no damn imperial units like savages here, you know? 30 centimeters, Dennis.
30 centimeters.
All right. How wide would you say it is? Just, you know, rough and ready.
About 9 centimeters.
Let's just go with 10.
10. All right.
Yeah, okay. You're not wrong, but I bet a space boot's a little bit thicker than my Chelsea boot here, right? So let's say, just also, Dennis, to keep the numbers simple, 10 centimeters by 30 centimeters, okay? So what do you get if you multiply 10 centimeters by 30 centimeters?
300.
And the units?
Centimeters squared.
Very good. 300 centimeters squared. Now, this is the radius of the moon in kilometers. We should probably convert that to centimeters. Does anyone remember how many centimeters are in a kilometer? We did it several times in our last class.
No, I gotta catch up.
All right, I'll let you, yeah, someone else. Like, Michaela's kind of babysitting. Oh, there's Brandon. Hey, Brandon, how many centimeters are in a kilometer?
Shit.
What'd you wake up late today?
Yeah, really late.
Okay. Well, I kind of had a hard time too. So I guess you'll have to wait for the recording, right?
Yeah.
All right. In our last lecture, Megan, help me find it. You're good at finding things in your notes. How many centimeters per kilometer?
Hold on. Did we do it in our homework?
We did it in our homework. We did it in our lecture class. We converted a bunch of times. Like when we did the density of a planet, we had to convert from centimeters to kilometers a bunch of times.
I have 1 kilometer. This could be so wrong.
It could be so right though.
10 to the 5th centimeters.
Okay. It's 100,000 centimeters per kilometer. So what's the radius of the moon then? Punch them up. It's going to be 1.7 times 10 to the something. What's my power?
Is it 8?
Yes. Okay. So the probability is the area of the boot, 300 centimeters squared, over 4 times pi times 1.7 times 10 to the 8 centimeters squared. Could you guys punch that for me, please? And punch it quickly so that we can get done our homework.
I got 4.0 times 10 to the 10th.
Megan, you need to divide by 4 and divide by pi and divide,
You're right.
right?
Yep.
Okay. Anybody get something different? Michaela, Tess? Michaela, just read it out to me. Oh, can you read it out to me?
Times 10 to the -7th.
Sorry?
I got 1.4 times 10 to the negative 7.
You forgot to square your radius.
Oh my god, this is a joke.
It's all right. This happens. What'd you get, Michaela?
I got a really, really small number.
Well, why don't you read me a really small number?
8 point, if you round, 8.3 times 10 to the negative 16.
Why would we have a really small number, Michaela? Why would
Because
this?
the footprint is probably really small compared to the area surface or the surface area of the moon. So
Right. The chances of hitting the footprint is wicked tiny, right? If you just the chances of hitting it with one impact is really tiny. Now, normally probabilities don't have units. If you toss a coin and the probability is 0.5, that means it's a 50% chance of getting heads, right? There's no units to that 0.5, it's a percentage. But that doesn't mean we can't assign units to try to help us think in terms of dimensional analysis. Let's assume that the area of the boot and the area of the moon, when we take the ratio, we're going to be taking the ratio. The area of the boot is proportional to the number of boot impacts or foot strikes, and the area of the moon is proportional to the number of moon impacts or moon strikes. The ratio of this could be thought of the ratio of the number of foot strikes to the number of moon strikes. Now, we've been given two numbers to work with, 25 million strikes per day and 20 strikes. Are the 25 million strikes per day foot strikes or moon strikes? What do you think?
Would they be foot strikes?
Well, in the reading of the problem, Dennis, it said the moon is struck by 25 million impacts per day.
All right.
It did not say the foot is struck by 25 million impacts per day, right?
Oh, then moon. Yeah, moon strike.
So these are moon strikes per day. The foot needs to get hit by 20 foot strikes to be destroyed. So how can I do dimensional analysis to find the number of foot strikes per day? I want to take this number and do something to it unit-wise to find out the number of foot impacts each day. What should I do? I'm going to erase this bit up here. We have 8.3 times 10 to the minus 16. Sorry. Yeah. Foot strikes for every moon strike. So what do I want to do? How can I combine that with these numbers to get the number of foot strikes per day? Well, come on. You could do this. Dimensional analysis.
I'm just a little confused. Would we use the numbers in the probability at all, or?
Well, this is the probability, but we would want to use the other numbers given with us.
The other numbers given.
You have foot strikes per moon strike,
Yeah.
25 million moon strikes per day, and 20 foot strikes to destroy the foot. I want to combine some numbers to come up with the number of foot strikes per day. So what do I do?
Would you put 20 on top? No.
On top of what?
Like on the top bar, like 8.3 times 10 to the negative 16, and then 20.
But if you multiply that by 20, you're going to get foot strikes squared per moon strike. That's not helpful. I'm trying to get foot strikes per day.
I'm kind of just throwing shit out there, to be honest with you.
Well, if you're trying to get a per day, which number should we be using along with our probability?
25 times 10 to the 6.
Yeah, I thought that would be obvious. Okay, so Megan, how do I combine those two in such a way to end up with foot strikes per day?
Wait. Would you put the multiplication bar and then division bar, and then would you put 20 on the bottom and then 25 times 10 to the 6 on the top?
No, I was thinking, Megan, a lot more simply. If I have foot strikes per moon strike, if I just multiply by the number of moon strikes per day, then my moon strikes would cancel, and I'd end up with foot strikes per day. That's how I was thinking about it. 25 million to 1. What do you get if you multiply those two?
Um, 2.1 times 10 to the negative 8.
Foot strikes per day. Michaela, what does it mean if I have 10 to the minus 8 foot strikes per day?
That it's still a small probability.
This is not exactly a probability because it has units of per day. It's a frequency. What does it mean if your frequency is 10 to the minus 8 foot strikes per day?
That means that the footprint would be hit that many times per day.
But that many times is less than 1 times.
Yeah, so it wouldn't be hit.
In a day, right?
Yeah, it'd take longer than a day.
How much longer? I bet you could figure that out.
It would take.
What do you do if you want to, suppose you wanted to know the number of days per foot strike, what would you do then? Suppose instead of knowing the number of,
You would have to move the decimal point to the right 8 places on 2.1, right?
Multiply the 2.1 times 10 to the negative 8 times the number on top, the 8.3 times 10 to the negative 16.
no, you've already used that number to get this one. You don't want to go backwards again. If you have units of foot strikes per day, but you'd rather know how many days to get 1 foot strike, How do you fix that? What do you do?
Can you repeat that?
Yes, you have foot strikes per day. You want days per foot strike. What do you do about it?
It sounds more complicated than it probably is.
Yeah.
Yeah, I think the wording is a little confusing.
Okay, so that may be my fault then. And I'm willing to.
Would you have to multiply instead of divide?
You have to do a different operation. You want to flip your units. You can clearly see that there's less than 1 foot strike per day. So if you want to know how many days to get 1 foot strike, instead of knowing that it's 2.1 times 10 to the minus 8 foot strikes per 1 day, you simply take the reciprocal and you take 1 day divided by 2.1 times 10 to the minus 8 foot strikes. And that will tell you the number of days. So do that for me. You can even use your bloody reciprocal key by hitting Shift 1 over X, which is the close parenthesis key. So why don't you do that? Could someone take that reciprocal for me? Something's weird. Oh, I get it. What do you get? Guys, just take the reciprocal for me. Come on, I'm dying over here. Megan, could you just read it for me? You have the right answer. Just read it for me.
I'm going to put it in,
Is it bigger than 1,000,000? Then yes.
yeah. So 4.8 times 10 to the 2, 3, 4, 5, 6, 7.
Units?
Days.
Per foot strike.
Okay.
How many days does it take to destroy the foot? I'm sorry. Wow. Let me ask that better. How many impacts does it take to destroy the foot? Something's real weird. I don't know what's going on.
48 million?
No, no, no. Just read the question again. It tells you how many impacts to destroy the foot.
20.
20. So if this is how many days to get 1 foot strike, if we multiply by 20, we'll find out how many days to kill the foot. So we do 4.8 times 10 to the 7 days per foot strike times 20 foot strikes. And that gives you the total number of days. Why don't you guys do that for me?
I got 9.6 times 10 to the 1, 8.
9.6 times 10 to the 8, what?
Days?
Yes. How many years is that? How do you convert that from days to years?
You put 1 year on the top and
Yep.
65 days at the bottom.
What's that give us?
Um, 2.6.
Uh-huh.
The 1, 2, 3, 4, 5, 6.
Units?
Wait, what are we figuring out?
I don't know. I got
Years.
confused.
It'd be years.
Years. Which is the same as 2.6 million years. Neil Armstrong's boot print will continue to sit in the lunar regolith for the next 3 million years, undisturbed by any wind or rain. That's kind of a tough problem. Most of you guys are not familiar with doing probabilities, but that was a little introduction to how to think about it. Dennis, are you still writing?
No, I was just using my calculator.
Okay. Megan, are you still writing? Okay. I'm going to erase now. All right, 59. Dennis, you want to read that?
Yeah, sure. I just have to refresh my screen real quick.
Okay.
Sorry about the delay. All right, so 59. Okay. 59, it's called internal versus external heating. In daylight, Earth's surface absorbs about 400 watts per square meter. Earth's internal radioactivity produces a total of 30 trillion watts that leak out through our planet's entire surface. Calculate the amount of heat from radioactive decay that flows outward through each square meter of Earth's surface. Parentheses, your answer should have units of watts per square meter. Compare quantitatively to solar heating and comment on why internal heating drives geological activity.
How many zeros are in a trillion?
12?
Very good. So 30 times 10 to the 12 watts are what the radioactivity of Earth provides. And we're trying to figure out, as that radioactivity leaks through the surface, what are the number of watts per square meter flowing out of the surface of Earth? and we want to compare that to the sunlight that's beating down 400 watts per meter squared. To do this, we are going to employ the inverse square law, because watts per meter squared are what we call the brightness. And the brightness is the luminosity, or the power, over 4 pi r squared. The radius of Earth is 6,400 kilometers. And I'm going to quickly convert that to meters by doing 1,000 meters per kilometer. That will give me 6.4 times 10 to the 8 meters. I can then calculate the brightness by doing 30 trillion watts over 4 times pi times 6. Oh, did I say 10 to the 8? 1, 2, 3, 4, 5, 6. I apologize. It's 10 to the 6 meters. 6.4 times 10 to the 6 meters squared. Why don't you guys calculate that for me?
I got 0.06
Units?
watts per meter squared.
Okay. Excellent. Now, the concept is that this is a lot less than solar heating. This is 400 over 0.06 is approximately 6. This is like 6,000 to 7,000. This is 6,600 times less than solar heating. But the idea is that, however, geothermal energy still drives planetary geology because the energy must flow across, let me do that up here. The energy must flow across the lithosphere through conduction. Whereas the solar energy,
Professor, do you mind adjusting the camera?
sorry,
Thank
must
you.
flow across the lithosphere through conduction, whereas the solar energy is re-radiated back into space. Sunlight can only penetrate down about a meter into the ground at best. Even that's kind of ambitious. But the geothermal energy flows across hundreds of kilometers of lithosphere. Energy tends to leak from the inside of a planet out. If sunlight drove geology, then Mercury would be the most geologically active planet in the solar system. All right.
Can you just keep that up for 1 sec?
Shoot, betcha. Actually, I was going to suggest our last homework problem is wicked easy, and I might be able to work it into my lecture today when I talk about plate tectonics, if that's okay with everyone.
And I can see right after it says still drives planetary geology because it's at the very bottom. Yep.
And then I actually continued it up here.
All right, yeah, I'm right
The
there.
energy must flow across the lithosphere. Does that help?
Yep. All right, I'm good.
So class, let's take a little 10-minute pause and I'll work the final problem into our lecture today. Does that sound good for everyone? You like that little pause? I could use a little snack to power me through the lecture, okay? So at 12:15, we'll get back to it. See you in a sec. Hello, everyone. I'm back and I'm caffeinated. So in today's lecture, we're going to continue to learn about planetary geology, and then we're going to shift into the topic of planetary atmospheres. Let's take a look at some key ideas from last class. Oops, sorry. In our last lecture, we learned that there were two ways to layer the Earth. A method on the left, which is layering by density, and that tells you what the planet is made of, what its chemical composition is. Usually it's a mixture of rock on the outside and metal on the inside. The other concept is to layer a planet not by the density, but instead by the strength or the rigidity. And when we do this, the outermost layer, which is the frozen, brittle, crispy layer, is the lithosphere. On Earth, that sits on top of a warm, convective asthenosphere, and then even warmer layers of solid and liquids below. So when we do this and we compare the planets, we see that while all planets have a composition that is rock on the outside and metal on the inside, not all planets have the same depth of lithosphere. Planets like Venus and Earth show a thin lithosphere, while the smaller terrestrial planets show a much thicker lithosphere. In class, why are the planets that are smaller thicker in lithosphere?
Because they're colder?
Yeah, they've cooled off more. We encapsulated that in something called the surface area to volume ratio in our office hours today. And I'll give you a quick review of the concept. Well, before I do that, let's ask this question. Let's compare heating and cooling methods in a terrestrial planet and see how they do this. This cheesy slide shows us how planets gain internal heat. Sources of heat in a planet include 1, accretion. I think I did this slide last time, but let me just kind of do it again as a sort of refresh. So there's accretion, which is basically the heat of formation. There's something called differentiation, which is a big concept in planetary science. That's kind of a $10 word there. Does anyone remember what the differentiation of a planet means? What does it mean for a planet to be differentiated? Do you guys have notes on that, or? It's got something to do with these little teardrops. What do the teardrops represent? You know, this girl I used to date, she likes this really terrible drink. It's called a pineapple upside down martini. It's vile. It's some sugary concoction.
That sounds awful.
Yeah, well, I mean, different strokes for different folks, but let's see if we can find a picture of a pineapple upside down. Oh, I guess there's pineapple upside down cake too. Let's start with the martini because that's funnier. When you put these different things in, it looks like this. I would say that a pineapple upside down martini is a differentiated drink structure. What do I mean by that?
Because the liquids are separated. Well, I guess not really liquids, but
Right. So I guess,
it would be like juice to alcohol, technically.
or pineapple juice to, I forget what this syrup is or something, right? Or maybe it's like a syrupy liqueur. I can't remember. So what's that got to do with the layering of Earth then?
It's like the rocks, the different rocks, right? And how they move.
Well, it's not just rocks though.
It's dense material.
What are the dense materials inside of a planet? What is a terrestrial planet made out of, Brandon?
Oh, we have that in our notes. I just looked at that.
Is it made out of, you know, pineapple juice and creme de violette or what?
Metals and silicates.
Okay, so which ones are heavier?
That would be metals.
Okay. How does that generate heat?
By moving.
And by rubbing together, right?
Yeah.
That's friction. Okay. Differentiation means heavy metals sink, whereas light silicates like rock rise. And the third method, which we talked about briefly in our office hours today, is radioactivity. Radioactivity involves the decay of radioactive isotopes, which generate energy. And lead to internal heat. So did we show you guys a little physics animation last time for radioactivity?
No.
Do you remember that?
No.
Let's do that because it's kind of cool. I've got these physics Java apps and they kind of make the day fun. And there's one on nuclear fission. The sun uses fusion as its nuclear energy, but the type of radioactivity that powers the interior of a planet is radioactivity from fission, where you break apart a big fat nucleus like uranium-235, right? So here I am, I've got a U-235 nucleus. It's somewhat unstable, and I'm just going to agitate it by hitting it with a high-speed neutron. It builds up internal energy and boom, it pops. It breaks apart into daughter nuclei and releases a gob of energy. Maybe I could get a few of these guys up here. Let's make ourselves a few U-235s and a few U-238s, and let's just hit one of these with a gun and see what happens. Boom. Each radioactive isotope kind of triggers another, and you can, I didn't quite get to a chain reaction there, but I could if I introduced more radioactive isotopes. You know, radioactivity is in the ground rock all around you, even in the bedrock of Rhode Island's granite. I think you smoke the equivalent of 2 Marlboro cigarettes per year, whether you want to or not, just from radioactivity in the ground rock around you, especially in the form of radon, but there are other isotopes as well. You guys remember The Simpsons, and Homer Simpson's job was to work in a nuclear reactor, and his job was to control the control rods, which adjust how much nuclear radioactivity is allowed to propagate through these nuclear rods here. So you fill them with an enriched type of uranium. If you open the rods up all the way and you fire the neutrons, you're in danger of getting a runaway nuclear reaction where all of the radioactive nuclei trigger each other and you basically have a complete meltdown like Fukushima. That's not very good. If you put the control rods all the way up, you fire only a little bit of neutrons and they kind of peter out. The trick is to sort of fire the neutrons and control the rods so that you don't let the nuclear reaction get out of control. You can kind of generate a steady amount of power that you see over here. And that's Homer Simpson's job in The Simpsons here, right? Is to kind of control these, this nuclear rod. Now, you can generate quite a tremendous amount of heat because even though there aren't a lot of radioactive isotopes, the Earth is very big. One device that you might use to measure radioactivity would be this guy here. This is a Geiger counter. Radioactivity takes the form of alpha, beta, and gamma radiation. Did we talk about that at one point? These were first discovered by Madame Curie in the early 1900s.
Yeah.
Do you remember what the different particles mean? Like, what's an alpha particle? What's a beta particle?
I don't remember that, but I remember she killed herself. Well, basically because all the radiation.
She didn't kill herself.
Yeah.
Radiation killed her.
Yeah, but like, yeah.
It was not a voluntary death because she was investigating these. She didn't know about radioactivity in Teenage Mutant Ninja Turtles. She was the one who discovered it, right? The way this works is this wand will pick up, alpha particles are helium nuclei, beta particles are electrons, and gamma rays are little photons. And this wand can detect, I believe, all three. And if I turn it on, you should be able to hear some clicks here. Ooh.
Can that device detect stuff from like computer screens and phones and stuff?
Computer screens don't give off particle radiation. They give off electromagnetic radiation in the safe part of the spectrum.
Okay.
This detects the dangerous radiation. Listen to the clicks. There's not too much radioactivity here, so you can hear an occasional click, which means occasionally alpha particles are hitting your forehead while you sit there in your room. Ooh. I wonder if I'm radioactive anyways. Uh-oh. Okay, let's try a test charge, shall we? Hold on, let me get my phone. I want to show you guys some stuff. Get the Wi-Fi on here. And let's share screen. My phone. Okay, so my device came with some test charges. Probably shouldn't put them too close to my coffee, but here are some test charges here. This one is cobalt 60. Let's see what happens. Let's listen to the clicker here. Can you guys hear that? Ooh, cobalt 60 is hot. Here's polonium-210. That's what the Russian secret agents used to poison the dissident living in the United Kingdom. Lyshenko, was it? Anyways. This one has a short half-life, so it probably is all spent.
Are those aren't that radioactive, are they?
A little bit. They're not too radioactive, but
like it's not enough to hurt you, essentially, right?
well, speaking of that, I mean, all radioactivity can hurt you. It's time, shielding, and exposure that prevent it. I actually have something cut. Oh, sorry. I've got something kind of cool that I want to show you. Watch this. I hid it somewhere. I tried to hide it as far away as possible. What did I do with the damn thing? Hold on a second, guys. I need to put my phone down for 1 sec. Just look at my ceiling for a second. In the Can It Hurt You department, Brandon, when I was in college, my friend who's a chemist went to this kind of swap meet out in the desert where you could pretty much buy anything that you could imagine. And he got me a birthday present, which is a rock of uranium ore called carnotite. And I want to show you what this looks like. Carnotite is a mixture. Do you see how yellow that is?
Mm-hmm.
It's a mixture of U-238 and 235, but this is basically what they make yellow cake out of. Do you see how crazy yellow the top of that rock is?
Yeah.
That's all uranium ore. Now, here's my Geiger counter here. Let's see what happens when we put the Geiger counter up to it. Now, I need to like show you for effect here. So I want to keep this clicker close so you can hear it. That, Brandon, is dangerous radiation.
Yeah, that's that's a little.
Not to worry. The guy who sold it to me assured me that this plastic box is perfectly capable of blocking the alpha particle radiation.
Yep.
Then I attempted to buy a shielded lead box to protect myself. I thought it was a lead box. It turned out to be a lead foil lined box. Let's see what happens here. So I'll.
It's still clicking. It's so funny.
Yeah. That's why I hid it over there in the corner of my room.
Oh yeah, it really protects you, doesn't it? Oh God.
I used to keep this in my office, in my desk drawer. And when my office mate found out that I had a rock of uranium in the desk drawer, she got really, really angry at me and made me remove it. Now I try to keep it in the far corner of my room.
Oh God.
Yep. So, yeah. Probably not the, anyways, think about it. That's one rock of some type of sandstone from Arizona. Radioactivity is all around us. And it generates a significant amount of thermal energy. This can actually keep the interior of our planet warm for billions of years. What about ways in which planets cool off? Honestly, if you ask me, there's kind of only one method that a planet cools by. Sorry, this is an iPhone share. Let's share my screen over here. The book presents it to us as 3 different cooling processes. They have convection in the Earth's mantle. This is rock that flows with warm bubbles of light materials rising and dense bubbles sinking. That's the differentiation process. Conduction occurs across the solid lithosphere, just like you're heating a frying pan from below. And then at the surface of the planet, it's radiation, radiating into space. Those are the 3 methods of heat transport, and they're all involved in transporting heat from the interior of Earth to the surface. But if you were to ask me, how does a planet actually lose energy? I would say it's by the 3rd method, or by radiation. Planets cool. I don't know if I did this last time or not, but a planet shines away its light over time like a black body. The planet is a hot, dense, solid. And that means it will shine away light. In the case of Earth, Earth's average global temperature is 15 degrees Celsius, which if you convert that to Kelvin, you've got to add 273 to 88 Kelvin. You can first calculate the brightness of Earth. The brightness of Earth, if you consider it to be a black body, is sigma t to the 4th. And that's 6 times 10 to the minus 8 times 288 Kelvin to the 4th power. You get pretty much your 410 watts per square meter, which is very close to the amount of energy you get from the sun, but plus a little bit extra. And the meaning of that is that it's basically sunlight that heats the surface. But a bit of that extra energy is coming from geothermal energy leaking from below. And the peak wavelength of emission can be found from Wien's law. 3 times 10 to the 6 nanometer kelvins divided by the temperature. If you plug in 288, 3e to the 6 divided by 288, you get about 10,000 nanometers, or 10 micrometers is the peak wavelength of radiation. And that is squarely in the infrared. The meaning of that, of course, is that planets shine away their light into space in the infrared regime. Planets shine themselves cold over time. That's how planets lose their internal energy, by shining away infrared light into space. In that sense, they're quite similar to a baked potato on a windowsill, which might also shine its way into space through radiation in the infrared.
Professor, I have a, it's kind of really off topic, but it's because of nanometers.
Okay.
Can because I was reading something where something was like had a thickness of like nanometers, but I thought something can something be the thickness of nanometers?
Yes, many things can.
Because they said an obsidian, like, you know, obsidian knives that they make, it was saying it was so sharp that it could split atoms instead of tear like a normal knife.
Well,
I don't.
look, no.
Yeah,
Whoever
that's what.
said that was a liar. Listen, in some ways, when you cut something, you are splitting atoms, right?
Yeah.
Because you're cutting through molecules. But to split an atom means a nuclear reaction. So maybe in a comic book, you could have a nuclear knife that would poke an atom and cause a nuclear explosion.
Yeah, that's
That sounds like someone telling tales out of school, right?
Yeah.
I don't know exactly how they explain that, but if you cut a banana, you are cutting through molecules, right?
Yeah.
That's just exploiting people's ignorance of science.
Exactly.
However, saying that you cut atoms is pretty much a lie, you know?
There would be what, a nuclear reaction, right?
Yeah, that would be a nuclear reaction.
And that's no
By the way,
bueno.
can I just clear up something that maybe you said earlier, but is a common misconception? People think like cell phones and computer screens are giving off nuclear radiation. Nothing could be further from the truth. Computer screens give off electromagnetic radiation, obviously in the visible, that's how you see the light from the computer screen. And they give off some infrared from their warm electronics. And they give off some radio waves when they communicate by
Wi-Fi?
Wi-Fi, thank you. But that's not the same as nuclear radiation, right? That's not alpha, beta, gamma rays that killed Madame Curie. That's a totally different side of the electromagnetic spectrum. Gamma rays are on the short wavelength side of the electromagnetic spectrum. Visible, infrared, and radio are on the long wavelength side. Those wavelengths are safe and harmless. You're not going to nuclear irradiate yourself by looking at a computer screen. Okay, cool. So fun topics of discussion all. So if planets cool themselves down over time, that means there's something called a volume to surface area ratio. The idea is that the volume of a planet is proportional to its heat holding capacity the surface area of a planet is proportional to its cooling rate. And if you take the volume to surface area ratio of a planet, you get 4/3 pi r cubed over 4 pi r squared, or 1/3 times the radius. The meaning of which is this: bigger planets, planets with larger radii, stay hotter longer than smaller ones. Okay, friends. Can you tell me what that has to do with the picture of the lithospheres that I showed you earlier? How would that be relevant to this diagram? Can you guys help me figure that out? What do you guys think? Bigger planets stay hotter longer. How is that related to this diagram? How is it related to the lithospheres in particular?
Because the bigger planets have a smaller lithosphere.
Yes, was that you, Michaela?
Yeah.
Very good. The bigger planets like Earth and Venus have a thinner lithosphere. Smaller planets like the Moon, Mercury, and Mars have thicker lithospheres. So, Michaela, since you and I are talking, can you then connect that to this picture here of the surfaces of the 3 planets that I showed you? This is the surface of Venus. This is the surface of Earth. And this is the surface of Mars. What do those lithosphere thicknesses have to do with these surfaces? How do you know that this is the surface of Earth? What tells you that this is Earth?
The continents,
And continents would be related to what geological process?
tectonic plates.
So you can see that it's Earth just by the visible demonstration of plate tectonics on the surface. Do you see continents like that on Venus?
No. Well, kind of.
Not much
Yeah.
though, right? It's
Yeah.
not as defined. That means Venus doesn't really seem to have robust plate tectonics. How about Mars?
There's just a lot of craters. So would that be erosion, technically?
Craters are not erosion. We should probably distinguish the two in a few moments, but craters are their own form of thing. Like erosion, craters do destroy surfaces, but erosion is caused by wind, water, ice. Craters are rocks from space.
Is that one big tectonic plate right there, or no?
You know, that's an interesting thing. You could look at it that way. You've heard of Pangea before, right?
Yeah.
It's possible to consider, darn it, where's my, I had,
So wherever your mouse was hovering, it kind of looked like it a little bit.
if you think about the way Mars looks from a global standpoint, Mars kind of got arrested in like a global Pangea state. It's like one big continent at the bottom, and it's like an ocean up at the top. You kind of have to see the whole map, right? The northern hemisphere is basically like a big ocean or a dead ocean, and the bottom is just one big landlocked region. So you could think of Mars as being one big continent, but its surface is just riddled with impact craters. What does that have to do with those thin lithospheres that Michaela was talking about? Or thin versus thick lithospheres? What's the connection between the surface features and the lithospheres?
Warmer planets, it's more defined.
What's more defined?
I guess it would be the surface, right?
Well,
Or-
describe defined, because there's some defined features here too, right? That might be a
Yeah.
little too vague for me. But the warmer planets have what? The colder planets have what? Cold planet versus warm planets. What's the difference?
Warm planets have tectonic plates.
Well, Venus doesn't really have tectonic plates though.
Shit.
But you're getting warmer, shall we say.
More smooth?
More smooth is the right answer.
Oh, holy shit.
What makes planets smooth versus cratered?
Atmosphere, technically, because it would burn.
Well, not exactly.
I'm sorry. I'm just throwing shit out right now.
All right, then let me help then, okay? Maybe I need to do my job here. More internal heat drives more active geology. What do I mean by active geology? I mean stuff that is not impact craters. Active geology includes volcanism, includes plate tectonics, and it includes erosion. If a planet is cold, these things stop because they can't break through the thin lithosphere. That means slowly the planet gets covered over again by impact craters. So, active geology requires a thin lithosphere. It also implies some other interesting concepts. And that is that cold planets get covered by impacts over time. I want to show you two craters from Earth's surface. I think I mentioned this to you last time, but when I was in Arizona for college, I was fortunate enough to be able to take a trip out to Meteor Crater in eastern Arizona. And Meteor Crater is just a really impressive impact site. Here's a big, here's a nice high resolution picture. This is what it's like if, did I tell you that it's on private property and I tell you that whole story? To visit Meteor Crater, you have to go out to this extremely barren part of the desert and drive up this road onto a dude ranch. It's actually on private property. And they sell you tickets to see the crater for like 20 bucks. But I'd say it's worth it because for 20 bucks, you can stand at the edge of this observation platform and look down onto this thing and just be amazed at how epic this impact crater is. They make you go through a little gift shop beforehand, and they try to sell you like UFO keychains and things like that. It's pretty wild. So if you compare Meteor Crater here Let's find another picture, another aerial picture of meteor crater. Oh, wow. Here's a couple getting married at meteor crater. That's pretty hilarious. I dig that. That's weird. I like it. Here's yet another picture of meteor crater, okay? This is probably what it's like in the driest part of the year. I want you to compare this to another crater that is found in Australia called the Wolf Creek Crater. Suppose I asked you to contrast the two craters. Here's a picture of Wolf Creek Crater, and here's a picture of Meteor Crater. Can you tell in which ways they're different?
Meteor crater has a deeper impact zone.
Yeah, they call that the basin. So can you tell which one is older, Brandon?
It would be the other one, not meteor crater,
Yeah, why?
because it's filled.
What filled it in?
Shit. Where's that word? Would it be differentiate? No.
Differentiation happens way inside the interior of the planet. We're talking about the surface right now. What's going on with the rim of the crater?
It's green.
Well, forget about that. That's just about what part of the year it's in. Maybe I need to have two identical pictures. Let's find it in the middle of a desert season. No, it's not that it's green. It's something else. Okay, Wolf Creek Crater, Meteor Crater.
It looks like it's like worn down.
What would be wearing it down, Michaela? I can't think of it.
Would it be kind of like erosion, like how?
It would be
'cause, like,
exactly like erosion. This basin is filled in because erosion has been washing sand and silts down into the basin, filling it up. The rim, the mountainous like rim, is being chipped away by wind and rain that occasionally fall down in the deserts of Australia.
Is that crater bigger than the meteor crater?
That's a really cool question. I know Meteor Crater is a mile in diameter, which makes it 1.6 kilometers. Wolf Creek Crater is smaller, actually, right? But it's actually not much smaller. It's 800 meters, which is almost 0.9 kilometers, right? So they're actually quite close to each other. Wow. You know what's interesting? This crater is only 120,000 years old, whereas Meteor Crater is actually quite older than that. That's pretty wild.
So does that mean meteor crater is older? What? Hold on.
Yeah, I did not know that. I would never have guessed that. Holy cow. That really throws me for a loop there.
So what I said about the other one being older was wrong.
I guess so, but I didn't know that either. 150,000 years old versus Meteor Crater. That's crazy. So that could be differences in the amount of erosion in Australia versus the deserts of Arizona, which are quite dry, right? The desert of Arizona may have preserved that. But that is very contrary to the point I was making, and very, very strange. according to this, oh, okay, no, I'm sorry. I guess this is a lot, no, the problem was this is younger than I understood. So no, the point is still correct. We have 50,000 years for Meteor Crater, and we have 150,000 years for Wolf Creek Crater. So Brandon, the point is intact. The place that I got confused is that I thought Meteor Crater was older than 50,000 years, okay?
Perfect.
So we can draw a really important conclusion from that discussion, Brandon, which is, it's something like this. The first point is all planets, not just the moon and Mercury, get hit with impacts. So every planet has to have been hit with equal frequency. The size doesn't matter. And that's because while it might be true that Earth is bigger than the moon, both Earth and moon are microscopic in comparison to the radius of the solar system itself, and therefore they make pretty wimpy targets. Given enough time, however, they will eventually be hit by rocks in space. But if you look at something like the surface of the moon, which we did in our last office hours, the surface of the moon is covered in massive impacts. Do you guys remember how big Plato was from your lab last week? It's bigger than the damn state of Rhode Island. It's like 60 kilometers across, I think, if I remember correctly. You don't see kilometer-sized craters on Earth. But that doesn't mean that they haven't been hitting Earth. It just means that they're not there anymore. Why not? Because active geology erases impact craters. They get worn down by erosion or covered over by volcanic eruptions. And therefore, we can draw another conclusion. Another conclusion is that the density, and this is a very important planetary science conclusion, the density of impact craters is an indicator of the surface age of a planet. And this cannot be overemphasized. It's the #1 technique that planetary scientists use to make an estimate of the age of a planet. If there is a high crater density, we say that the surface is old. If there is a low crater density, we say that the surface is young. That's the #1 technique we're going to use for our labs today. Okay, with the remaining time that I have before tea break, I want to try to break down the 4 geological processes for you and just say a couple of quick words about each of them. It's going to be hard to do this in a half an hour, but I have to try. I'm going to erase all right. So let's talk about the 4 geological processes. And we'll begin by talking first about impact cratering. And let's come up with a few basic concepts of terms. Basically, when you have an impact, you have some type of rock from space, which is flying down to make an impact with the surface. And they have tremendous amounts of kinetic energy associated with them. Kinetic energy is related to the mass and the velocity of the object. Typical velocities for an impact crater might be of the order of 15 kilometers per second. That makes it very, very fast. And their masses can depend upon how big they are. We'll talk about that in a moment. When they strike the ground with these tremendous kinetic energies, they usually leave behind an impact crater that has a couple of notable features. First of all, the hole in the ground, which gets excavated by vaporizing the material, that's known as the basin. And the top of the crater is known as the rim. And sometimes they feature a central peak, which you guys remember from last time is the slap back from the rock. And they can also show some ejected material. Sometimes people call it ejecta, the material that's been blasted out of the crater. The spokes are sometimes called rays. So those are some terms that you hear associated with an impact crater: rim, peak, basin, ejecta, and rays. A good rule of thumb is that the diameter of the crater is anywhere from 10 to 100 times the size of the impactor. The impactor is the weird rock that's going to strike the ground. And it usually meets a crater that's anywhere from 10 to 100 times the diameter of the rock. Sorry. By the way, if we look at the surfaces of other planets around our solar system, we can see different types of examples of material that got ejected from the craters. And I'd like to show you my slideshow to sort of emphasize that point. Somewhere over here, I have pictures of different types of impact craters. Here's a black and white photograph where you can see a basin, a rim, and you can see some of the ejected material laying about in a blanket surrounding the impact crater. Notice some parts of the ejecta have even been struck with impacts, and you can see the ray-like structure emanating outwards from them. Look at this ejecta. You can tell that the surface was either icy or muddy and kind of froze after it was splattered out of that impact crater there. So whether the surfaces are a bit more icy or rocky will leave different types of shapes or patterns. Now, suppose I were to ask the class, what is the difference between these three different words here? So words that come up when we talk about impact cratering are a meteoroid, a meteor, and a meteorite. And the difference between these three things is about where you find them in their journey towards Earth. A meteoroid is when the rock is found in space. And meteoroids could either be parts of an asteroid or parts of a comet. And for that reason, we don't want to say asteroid or comet because they could come from either object. Some meteorites even come from the surfaces of planets. So asteroid or comet, or it could even be a planet rock. Like some meteorites found on Earth are pieces of Mars. A meteor is when the object strikes the sky and it creates a big fireball called a bolide. Here's a fancy term for you. A bolide is a fancy term for the fireball that develops, at least on Earth, when it strikes the sky. A meteorite happens once we found the rock on the ground. So meteorites are rocks on the ground. Meteoroids are when they're in space, and meteors are when they're in the sky. It's too bad that we're not present together. I actually have a piece in my hand of the iron meteorite that struck Arizona and formed Meteor Crater. So I'm holding in my hand a very piece of the rock that was responsible for forming Meteor Crater. It's a wonderful show and tell item. What's particularly interesting about it is, and this is unfortunately something that you're not going to be able to experience, holding this in your hand, you really get a sense of how dense the material is. I guess I do have a little scale up here. I could try to demonstrate it. I don't know how many pounds this thing is here, but this only measures up to about 4 pounds. It's a letter scale. Okay, I guess it's 2 pounds. You really feel the density of a rock. It's not a very big rock. So I want to show you guys a cool a video. We occasionally do capture some of these impacts on a camera. Let me show you a pretty cool YouTube picture here, or a YouTube video rather. YouTube meteor police camera. In Canada, this police car was driving along the highway, and it captured a video of a meteor striking Canada in Edmonton. And it's just kind of interesting to take a look at this and to think about what's going on here. Oh, shoot. This is the video I want to show you. It's only 16 seconds long, so you got to watch quick or it'll disappear here. I want you to just watch this impact and think about what's going on. Now look at that. They're going to slow this down in the next frame here. Here it is a bit slower. The fireball, or the bolide, is so bright, it literally turns the nighttime sky into daytime. Why is the fireball so bright? It's heat and friction with our atmosphere. Sometimes it can even heat up internal gases inside the thing and cause it to explode over the surface. There are other cool videos of meteor impacts, like one that happened over Russia.
That one was crazy.
Did you see this? It
Yeah,
even blew out windows.
Yeah, everyone didn't know what was happening. They thought it was, yeah.
Let's see if we can see this here.
Anderson Cooper.
Anderson Cooper is
10 on CNN.
The images look like something out of a movie. A tiny asteroid tearing through space at a speed of 33,000.
He probably should have said meteoroid, don't you think? Okay, anyways.
Out of a movie, a tiny asteroid tearing through space at a speed of 33,000 miles per hour before streaking across southern Russia. Cameras caught sight of the white trail as it headed across the sky. And then this. An explosion of light, then a massive sonic boom. Strong enough to shatter windows and damage buildings. There were reports of more than 1,000 people injured, mostly from glass and debris.
So yeah, the shockwave blew. Oh wow, here's a Taekwondo studio. Let's see what happens here. Maybe they'll karate kick it.
This video shows a children's judo class. Windows blew out here and in buildings around the region. Some people said they thought it might have been a plane crash.
pretty wild, right? So people do occasionally, no one that we know has ever been directly struck with an impactor. Although I've got to show you a slide here. In one legendary case, where's my S drive here? In the 70s, someone's car got struck by an impact. I have this somewhere here. Oh. Was it this slideshow? Yeah. In the 70s, somebody's car got struck by one. We've never had a report of someone getting directly hit with one, but I suppose it's possible that such a thing could happen. This person had a bad day. They had a meteorite strike the back of their car. One of the most legendary ones was the so-called Tunguska event. This happened, I think, in 1908 in a very remote part of Russia, in Siberia, where a meteoroid exploded a few hundred miles above the surface of the Earth, and it caused a massive impact crater. Sorry, I think I was a little high there. It disintegrated at an altitude of 5 to 10 kilometers rather than hitting the surface. The meteoroid size was anywhere from 50 to 200 meters. The shock wave would have measured 5 on the Richter scale for earthquakes. This explosion would have been capable of destroying a large metropolitan area. Imagine if in 1908 that had hit New York or Paris. It took them a while to mount an expedition out to the area because it was in such a remote part of Siberia. But they found when they got there a bunch of knocked over trees and killed reindeer and some other stuff like that. It may have even wiped out some people, but they would have been, you know, I don't know what the equivalent of Eskimos or Inuits are in Russia, but some small population might have been out there. I wanted to show you a picture of the Tunguska event. I think the legendary picture of this thing is just of this expedition that went out there and found a bunch of blasted over trees. All right, well, whatever. A question that you might want to ask me is, how often do we get hit with meteoroids? And actually that question itself is not logical, because you can't ask how often do we get hit with meteoroids in general, because it depends upon their size. A better question is to ask, how often do I get struck with an impactor of size X? And this graph tries to show you the frequency with which objects strike a planet today. Every hour of every day, we get struck with objects that are 1 meter or more in diameter, but most of those just burn up in the atmosphere. After about 10 meters, they can actually make it down to the ground and create a small crater. At about 1 kilometer, they can get pretty big. You get struck with one of those every million years, and those are capable of creating tsunamis or devastation or climate change. And then once every 100 million to once in Earth's history, that's when you get hit with the big boy, a dinosaur-killing meteoroid capable of causing mass extinction and climate change. If we look at the history of Earth, we find that there are a number of so-called extinction events where many species on Earth sort of spontaneously died out in a very short period of time. Now, we don't know the exact cause of these extinction events, but many people hypothesize that a good fraction of them have to have been caused by impacts. Damn it. In this graph here, we're plotting the number of extinct species in millions of species as a function of time. Now, every hour of every day, things are going extinct on planet Earth. They could be something as complex as a dodo bird or something as simple as a bacteria. But extinction and life dies all the time, and species go extinct. But every now and then you get these kind of gnarly spikes where in a short period of 100 years or so, you get a big burst in the number of species that go extinct. the most intense of which was the Permian-Triassic extinction event, which is notable for having wiped out something like 90% of all organisms on Earth. I think it was 90% of sea organisms and 85% of land organisms. I don't know why the sea was higher than the Earth, probably because aquatic animals are sensitive to small changes in acidity and pH and things. But in any case, nature occasionally scraps her ant farm and builds up from the beginning again. And we believe that these spikes might actually all be correlated to giant massive impacts that have struck Earth. And while we're on that subject, let me tell you about something that gives me the willies. It's a YouTube video of a meteoroid or an asteroid you've probably never heard of, the orbit of 4179 Tutatis. 4179 Tutatis is an Earth-crossing asteroid that comes close to us about every 4 years. And about 7 years ago, this is what happened. Right around Christmas time. So let's take a look at this here. Here's 4179 Tutatis, and there it is doing a close flyby with Earth in December of 2012. Woo! Now this bad boy here, that's maybe 5 kilometers across or so. That's a big meteoroid. That's capable of wiping out more than a city and maybe even creating some climate change on Earth. Now we've calculated its orbit for the next 100 years, and we're 90% confident or 95% confident it won't hit in the next 100 years. But as you wind the clock forward, small uncertainties in the orbit measurement lead to bigger and bigger uncertainties of whether or not it will hit. So the probability drops with each 100 years out that we go. Probably at some point in the next 1,000 years or maybe tens of thousands of years, that thing will eventually strike Earth, and it will not be pretty. So you may forget that your time on Earth is limited, and even a whole species' time on Earth can be limited as well by the frequency with which these impact craters strike. In any case, all the planets, including Earth, are being hit. But the most important aspect of impact cratering is that the density of craters, I'll say this again, indicates surface age. Let me tell you about an interesting study that they did at the surface of the moon during the Apollo series. You guys will notice, actually, let's go back to that photograph of the moon, that the moon has 2 types of terrain, which are remarkably different from one another. The type of terrain that you see here, the smooth regions, are known as the lunar maria, which is Latin for seas. The types of terrain that you find up here or here, in fact, maybe up here, these are called the lunar highlands, like the Scottish Highlands. The highlands are clearly much more heavily cratered than the lunar maria. And when astronauts landed on the moon, they sampled and did radioactive dating of the lunar highlands versus the lunar maria. And they found this interesting result. So on the moon, the so-called highlands have a surface age of 4.6 billion years old. Whereas the lunar maria, which are some volcanic in origin, have an age of about 3.9 billion years old. But class, the highlands are very heavily cratered whereas the maria are quite smooth. And that presents something of a planetary mystery. Class, both of these surfaces are close to 4 billion years old. What I want to know is, why are the maria still so smooth today, 4 billion years after they formed, whereas the highlands are so incredibly heavily cratered? Why didn't we get enough cratering during those next 4 billion years to make the maria look almost the same as the highlands? Can anyone think of a reason why the density of impact craters is so much higher on the highlands than on the maria? I mean, it's a difficult question. But do you at least understand why I would not expect the maria to be so smooth today? Brandon, why wouldn't I expect the maria to be so smooth?
Because, I mean, the probability of that actually happening is slim, right? Or
Probability of what happening?
less meteors hitting it.
Right. You would assume that the same number of meteors struck up here that struck down there. It's not like
Yeah.
they all missed this zone, right?
Yeah.
Well, then why is it still so smooth billions of years later? We need a hypothesis or a theory to fit the facts.
Could it be because it's one big crater?
No, that's a shot. It's got to do with something called the heavy bombardment period. Let's take this as a note first. To explain why both of these are very old, but this shows a highly cratered surface, astronomers developed a hypothesis or a theory known as the heavy bombardment period. The heavy bombardment period is a concept which can explain why the highlands are so much more heavily cratered. And it means that in the early solar system, the frequency with which meteoroids must have rained down on the surfaces of the planets must have been much higher. Let's just call up a quick picture here of the so-called heavy bombardment period. It's a concept that billions of years ago, during the first billion years of our solar system's history, that there weren't just a few meteoroids striking Earth per day, but that there were many, many times more meteorites flying around the solar system, since it had just recently formed and it would have been riddled with rocky debris that didn't quite make it into the planets. These objects would then rain down on the surface, pelting the hell out of their surfaces and covering them with very, very dense cratering. It's thought that many of the giant craters that we see on the surface of the Moon and Mercury were all formed during the heavy bombardment period. But that after about 1 billion years or so, most of the major meteorites struck the Earth and things kind of quieted down. And today we have a much lower rate at which meteoroids strike the surfaces. So to define the heavy bombardment period, we would say it's a period in the solar system's history from somewhere from 4.6 to 3.9 billion years ago, when many massive meteoroids rained down on the surfaces of the planets, creating the heavily cratered highlands. We call these regions highlands on all of the planets, wherever there's heavy cratering. The heavily cratered highlands seen on Mercury, the Moon, and to some degree Mars. In some ways, the disparity between the cratering in the highlands and the cratering in the Maria, they tell us a little bit about the differences in the two types of terrain that we see across our solar system. And they explain why there are so many more craters on the surface of the Moon and Mercury than there are on Venus or Earth. Okay, class, I still want to discuss volcanism and impact cratering and erosion and even get into atmospheres. But at this point, if it's okay with you guys, we'll take a little sort of little lunch break, little tea break to refresh ourselves and keep things interesting. Is that okay with everyone? All right. Okay, yeah, there were more points I wanted to get to before then, but this is what I did. So let's pause, and at 2 o'clock, we'll come back and we will continue our lecture on planetary geology. Shall we begin our lecture? Or continue our lecture, rather? Okay. So I'm just going to say a couple words about geology, and then I want to start to get into atmospheres so that we can talk about the Jovian worlds in our final class. I'm just going to have the briefest of notes, much less than I would normally have, on the other geological processes, so that we have some context when we work on our Mars lab today. So when we deal with volcanism, we're looking at different types of volcanoes that we find around the solar system and the various ways that they manifest themselves. Of course, some of the most impressive volcanoes are the ones that we see on the surface of Mars, which is interesting because Mars isn't the biggest of the terrestrial planets that have volcanism. But interestingly enough, whereas the volcanoes on Earth often take the form of these pointy stratovolcanoes like Mount St. Helens or something, the volcanoes on Mars tend to be of a different variety. They tend to be massive shield volcanoes, like Olympus Mons, pictured here. Olympus Mons is actually the tallest volcano in our solar system. Part of the reason is that Mars has less gravity, and that means you can build up volcanic eruptions and build up taller and taller domes before gravity compresses them. The other reason has to do with the composition of the lava and how metallic it is, what type of minerals are present. It actually gets quite complicated, and there's an entire subsection of geology that deals with volcanism. We're going to look at some kind of broader strokes. I wanted to start by showing you a couple of interesting pictures. Here's a picture of the Cleveland volcano seen from the International Space Station. And this picture is interesting because it makes you realize that not only do volcanoes produce lava, they also produce tremendous quantities of gas. And this is very important from a planetary science perspective because it turns out that when planets form, they do not form with ready-made atmospheres surrounding their surfaces. Most of the planets were too warm when they first formed to hold much atmospheric gas. And also the protosolar nebula was mostly made of hydrogen and helium. And that's not what our atmosphere or the atmosphere of Mars or Venus are composed of. So it turns out that volcanism produces atmospheric gas, and over hundreds of millions of years, over even billions of years, this can lead to the development of substantial atmospheres around the terrestrial planets. I don't want to say something as simple as volcanoes equal atmospheres, but it's kind of close to that. So from our point of view, volcanoes involve a sort of structure, a vent in a thin lithosphere develops one of three types of volcano. There are stratovolcanoes found on Earth and Venus. These volcanoes are sort of pointy. And they're created by a sort of high viscosity lava, also known as basalt. There are shield volcanoes. We see them, so stratovolcanoes are found on Earth and Venus. Shield volcanoes are found on Mars, and in some cases Earth. Like for instance, Mauna Kea in Hawaii is a shield volcano. And these are the tallest, but they're also gradually sloping. They get their name from the development. They look kind of like a shield. And these are made from medium viscosity lava. And then there's a third type of volcanism that you might not think of as a volcano. These are volcanic plains. Volcanic plains are found on the moon, in some sense on Mars, and even on Earth in the form of the Yellowstone caldera. And these are basically what are basically just giant pools of low viscosity lava. Interestingly enough, although they may have started as some kind of a massive impact crater, the Maria on the moon are an example of volcanism more than they are an example of impact cratering. Maybe an impact crater originally started this process where it cracked through the lithosphere of the planet, but you can see at one point this was all probably frozen lava, and the lava was flowing downhill if there was a slight gradient to the crater site. And eventually this would have just filled up with a pool of lava which cooled off and solidified over time. The Yellowstone caldera today at Yellowstone National Park can be considered an active sort of volcanic plain. But you don't always have to have a dome to have a volcano. Let me tell you a few different terms that have to do with volcanism. It's kind of helpful just to kind of look at the diagram for volcano that we have on Wikipedia. They kind of give you a breakdown of some terms associated with a volcano that I think are somewhat helpful or interesting. Where's this bloody thing? They have a nice little diagram here. Let's click on this. So usually, if you guys can see down here, let me put you off to the side. We have a number of different diagrams here, a number of different parts to our diagram. We have a sort of magma chamber where we have warm, partially liquefied rock. a vent that comes up through the bedrock. The main opening through which the volcano erupts is known as a caldera. This is called the dome, and there can even be some side vents associated with our volcano. We won't do this in perfect detail, but we'll list a couple of the key features that you see here. Class, did everyone have enough time to copy this down? All right, I'm erasing that. So when I talk about volcanoes in our lab today, I'd like to be able to use a couple of fancy vocab words with you. So let's do a diagram of our volcano, just a simple one, okay? So we have the opening, and although not all volcanoes have this, this is called the dome. It's the mountain part of the volcano. This opening from which the lava comes, sometimes people lamely call it a volcanic crater, but the technical term is a caldera. It's a volcanic crater. I don't like to use the word crater because it's not caused by impact cratering. And then there can be a sort of central vent. There can be a large magma chamber. And there can even be side eruptions. This would be a side vent. Sometimes volcanoes blow out the side as well as the top. So that's not every part of a volcano diagram, but those are some key terms that you'll hear me use from time to time. Volcanoes produce two types of emissions, okay? Volcanism produces, obviously, one, lava. That cools to form a type of rock called basaltic rock. The planetary science effect of lava is that lava is going to repave the surface of a planet, which often erases impact craters and other geological features, and it smooths out a planet's surface. The second key effect associated with volcanism is what we call outgassing. And if you want to talk about the gases that come out of volcanoes, the gases that are produced are primarily CO2, carbon dioxide, H2O. Water comes from volcanoes in the form of steam. Diatomic nitrogen, small amounts of sulfur dioxide, and even argon and some natural gas as well. But I'd say water and CO2, these are the top two gases produced by volcanism. The idea is that outgassing CO2 and H2O, they can build up and help form planetary atmospheres. So volcanoes are connected to the formation of planetary atmospheres. Which of our terrestrial planets have atmospheres, students? I'd hope you know the answer to that question. Of the 5 terrestrial objects, who's got an atmosphere?
Earth.
Okay, duh, obvi. What else? Who else?
Neptune.
Oh my God. Oh my fucking God. Can I slit my wrists? I just want to take a razor and lie down and cut my wrists. Because Neptune, Brandon, is not a terrestrial planet. Okay? We're talking about the terrestrial planets. Mercury. Okay, that was a little mean, but honestly, so was saying Neptune. Neptune hurt my feelings. Okay? We're talking about terrestrial planets. Mercury, Venus, Earth, Mars, and the Moon. Which of these guys have atmospheres?
This is Venus and Earth
And
Mars.
that's right.
Yeah.
So the biggest of the terrestrial planets, these guys have atmospheres. These guys do not, right? All right, that's important. Oh, while I'm there, let me share a couple of. I don't have time to do notes on everything I want to do. I've got to try to be choosy, but it's hard because this stuff is all going to show up in our lab today. Let me show you the two sort of places. First of all, let's just look at some lava of different types. So volcanoes tend to come up in one of two types of places on Earth. We have something called a volcanic hotspot. And that's where there's convection in the underlying mantle that's pushing up sort of warm convective rock. And as it gets close to the lithospheric boundary, the lowest density materials like water and CO2 start to vaporize and turn into steam. And they kind of heat up and melt the surrounding rock. And the melting of the surrounding rock builds up this magma chamber. And then tremendous pressure builds up over the years until at some point we finally blow the top off this thing through gas pressure. And it just blows gas and lava out into the atmosphere of Earth. Now, because Earth has plate tectonics, which push the lithosphere of Earth around the underlying mantle, as these lithospheric plates drift over the convective hotspots, you tend to form a chain of islands. Like you can actually see in the ages of the Hawaiian Islands how drifting over a hotspot leads to what we would call an archipelago or something. I have just a little crappy, not a great picture here, but this is showing you the ages of some of the more dormant volcanoes or islands in Hawaii. The direction of the tectonic plate movement is exactly in the direction of the chain of islands, the archipelago. And whereas Mauna Kea is an area of active volcanism, the other islands no longer have active volcanoes. And you can see their age increases as you move from Hawaii way up towards Midway, which is even off this screen here. And that the elevation is also dropping. So erosion is wearing these volcanoes right back down into the sea. I don't know if you guys know this, but another site of active volcanism is currently forming off the coast of Hawaii. And there is a new volcanic island, which is still under the water, but in the next million years will start to poke its head out of the surface of the water. It's known as Lohi, and it's an underwater volcano, which is currently probably over the convective hotspot. So Hawaii is going to get a new island in the future due to the motion of these plates over the convection zones of Earth. The other place we tend to find a lot of volcanoes is at what are called subduction zones. And these are places where Earth's highly dense oceanic crust push material down underneath the lithosphere and trigger a whole bunch of volcanism along the edge of the continents of Earth. Oops, sorry, I wanted to keep sharing there. That's how we get the so-called ring of fire. The ring of fire shows us where the majority of Earth's active volcanism is taking place. And it tends to take place along a sort of zone all around the Pacific Ocean, where plate tectonics drives seafloor plates underneath the continents and triggers sites of active volcanism. So all along the coast of North and South America, the Aleutian Islands in Hawaii, Japan, Indonesia, all of these places are regions of active volcanism and they're also regions of plate tectonics. So on Earth, there's kind of this dovetail, literally a dovetail between plate tectonics and volcanism. Volcanoes are fed by plate tectonics. It's why Earth is so volcanically active. Let's pause that there. That's all I want to say for that for now. And let's just have a few words about plate tectonics, and I think that'll give us an opportunity to finish that last homework problem. Okay, so just a couple of words about plate tectonics. Plate tectonics is unique, a robust set of plate tectonics is unique to planet Earth. Plate tectonics form mountains, valleys, canyons, and even trigger volcanism. Plate tectonics are caused by the thin, oh, I'm sorry, I wanted to add one other thing to that list before I proceed. It's also the cause of earthquakes. There are versions of earthquakes on Mars and on Venus, but they're, well, at least on Mars, they're reduced in intensity.
Would they be called Mars quakes?
They would, and they, in fact, the Mars InSight lander, which is the most recent probe that we've landed on the surface of Mars, is basically a big seismograph, which is, or a little seismograph designed to measure Mars quakes. That's exactly the idea. So how would we get a set of plate tectonics, and how does this work? It's something that's frequently called the conveyor belt model. And before I describe how the conveyor belt model works, let me show you a little picture that we associate with plate tectonics and the conveyor belt, just so you can get a sense of what I'm referring to here. So here's a little diagram of how the conveyor belt works. Slide 63. The lithosphere is fractured into plates or big chunks. And the convection is in the asthenosphere, and the lithosphere floats on top of this layer of convective rock. And as convection causes hot bubbles to rise and cold bubbles to sink, it drives these plates around and smashes them into each other, sometimes in head-on collisions, sometimes at glancing angles. And when they collide with each other, they kind of stick and they build up pressure until the pressure becomes so immense that they either push up against each other and form mountains, or sometimes they snap in a violent earthquake and one plate gets shoved underneath the other into something like a convection zone. So one way we could describe the conveyor belt model is we could say that the Earth's thin lithosphere is fractured into a set of, I don't know, 10 to 12, they call them lithospheric plates, which sort of float on the convecting, here I'm going to mix my modes and I'm going to say mantle instead of the asthenosphere, the convecting mantle of Earth. Convection then drives the plates on a sort of conveyor belt at a rate of 1 to 3 centimeters per year, which seems slow. It is. It's the rate at which fingernails grow. But over hundreds of millions of years can add up to a significant amount of motion. Convection drives the motion of plates on a so-called conveyor belt at a velocity of 1 to 3 centimeters per year. Hold on 1 second, guys. I need a napkin here. The global implications of this is that as they drive around these convective plates, not only does they cause earthquakes, but this helps to form and even rearrange the continental landmass of Earth over hundreds of millions of years. Which is how we can get the continents seeming to fit together like a sort of jigsaw puzzle, and why we believe at one point the continents may have even been locked together in a global landmass called Pangaea, which then fractured apart. I'm assuming you guys heard of Pangaea at some point in one of your previous classes. Let's look at a couple of pictures. I want to show you an interesting slide that I like. It shows you the location of all the earthquakes that have been recorded over the last 100 years or so. The earthquakes are represented by tiny little green dots. Notice that the locations of the green dots are not randomly found around Earth. They're not uniformly spread over the Earth, but they follow the boundaries of the tectonic plates. And they kind of trace out where the plates are. The Pacific Ocean is on the Pacific plate. Notice that the North American plate consists of the continent of North America plus part of the Atlantic Ocean. So it's not continents floating on the ocean or anything silly like that. The continents and the seafloor are kind of connected to each other, and the plates are sort of something different altogether. Also notice that if you look along this region, which is known as the Mid-Atlantic Ridge, it's basically like a locus of underwater volcanism on Earth, and it's very fascinating. You can see that the continent of Africa and South America kind of fit together like a sort of jigsaw puzzle. It implies that at one point, these two continents were connected to each other, but they are being driven apart by an effect called seafloor spreading. Let's see if I can kind of find a picture of seafloor spreading for you. I think it's in the Earth chapter, somewhere around here. The concept of seafloor spreading is that warm convection is pushing up heavy enriched magma onto the bottom of the seafloor along the Mid-Atlantic Ridge. That volcanic basaltic rock is cooling down and forming part of the oceanic crust. And then as the oceanic crust pushed side to side, it drives other parts of the ocean floor crust down into convection zones under the continents, which then trigger a lot of volcanism. And they call this seafloor spreading. Let's see what some of the effects of seafloor spreading are by doing that final homework problem, which we didn't quite have time for in our office hours today. Okay, our last problem, which is a very short one, is for our homework number 8. Make sure you submit this one as well. And could someone please read me chapter 9, number 60, and we'll do it as an in-class exercise.
Plate tectonics. Typical motion of one plate relative to another is 1 centimeter per year. at this rate, how long would it take for two continents 300,000 kilometers apart to collide? What are the global consequences of motion like this?
So the plates are spreading apart. Sorry, my Africa and my South America don't look very good, but that's about as best I can do right now. The velocity of separation, did they say 1 centimeter per year?
Yes.
And what did they give us as a distance between the two continents again?
They are 3,000 kilometers apart.
Okay, the formula we're going to use to solve this is distance equals rate times time. We've been given the distance between them, we've been given the velocity, and we have to solve for the time. The time is the distance divided by the velocity. The distance is 3,000 kilometers. The velocity is 1 centimeter per year. What are we going to do about our units here? Let me write that again.
Do we turn it into meters?
Well, if we do that, we have to convert the velocity as well as the distance. I was thinking if we just convert like the distance into centimeters, then they'll cancel each other out and we can get to years. Right, Brandon?
Yep.
So how many kilometers are there per year? I'm sorry, whoa, that doesn't make any sense. How many centimeters are there in a kilometer?
Shit, didn't we have this?
Yeah, from earlier today. Anyone? Oh, please. Pretty please, the sugar on top. Can you find that?
1 times 10 to the 5th.
Yeah. Okay. So we should be able to do this in our heads. How many years is that going to be? How many years is that? This is supposed to be pretty easy, right?
Would it be 1 times 10 to the 8th?
Well, what about the 3?
Ah. 3 times 10 to the 8th.
Yeah, what's that number in plain English?
Millions would be 6. 300 million.
Good, and that's how I'd prefer to write it. Rather than 3 times 10 to the 8. What are my units? 300 million?
Years.
Okay, good. And Tess, what was the other part of this question?
So after we find how long it would take, it just wants to know what the consequences of the motion.
Do you know what they mean by the consequences? What does the 300 million years mean for Earth?
What do you mean by it?
Well, I'm intentionally being vague. I want you to figure out what they mean. They said, what are the consequences of this for Earth? What does this mean for Earth that it takes 300 million years for the continents to separate?
I know this is gonna sound dumb, but could the Earth like crack?
Well, the Earth is cracked.
Yeah. Shit.
It's not that you're wrong. It's not that it could crack. It's that it is cracked. And what's the difference between 300 million years ago and today?
Oh, what? Pangea, right?
Pangea versus not Pangea, right?
Yeah.
So one way we could look at this is we could say, let's write this down. This represents a geological time scale. And I want you to underline that. That's a key idea. The geological time scale over which Earth will rearrange, or we could have even said refresh, its surface. Like, you know how when I show you this picture, wait a sec. You know how when I show you this picture, you recognize it as Earth? If you wound this 300 million years back, or even 300 million years forward, you would not recognize Earth anymore. As a human of approximately 2020 Common Era, you will not recognize the surface of Earth hundreds of millions of years from now. It'll look completely different. You wouldn't even recognize it as the same planet. And it would probably look different in some other significant ways too, including the oxygen content, the types of flora and fauna found at its surface. Hell, 300 million years from now, humans are probably going to be gone. And there'll be some kind of hyper-intelligent dragonfly which rules over the Earth. Certainly the dinosaurs didn't expect to find a bunch of shaggy apes running the planet 300 million years ago. T-Rex was in control, right? Lizard people ruled the Earth. Who knows what it's going to be 300 million years from now? It can't stay the same. Okay, cool. May I erase? The last thing I'd like to talk about before I get into atmospheres is erosion. And we're going to keep erosion as simple and as dumb as possible, and just an interest to kind of get on with things. We're going to list a few types of erosion that we see around the solar system. One that is very important that we must not forget about is wind. Then there's water erosion. Water, as you know, can carve out canyons like the Grand Canyon, and it can wash away mountains. Ice is also a significant form, especially in terms of glaciers, which drag boulders across the surfaces of mountains and carve them out. We also see some weird exotic things in the outer solar system, which I would like to get to. Things like frost jets. Jets of ice that sublimate to gas, blow across the surface of a world, and then freeze out again. We tend to find wind erosion on both Earth and on Mars, but weirdly not on Venus. Venus doesn't have any wind erosion despite having an atmosphere. And that's because Venus has no rotation. It's the rotation of Earth and Mars that lead to winds, which kickstart erosion. Water is only found on Earth today. But in the past, Mars clearly had rivers, which you saw in that map of Mars from a few hours ago. Ice can be found on Earth, and in some respects on Mars, because Mars has some ice caps. Frost jets are found in weirder places in our solar system. They are found a little bit on Mars, but they're also found on places like a moon of Saturn called AS1010, and to some extent on Pluto, and a moon of Neptune called Triton. But frost jets are sort of in the outer solar system, so we've got a little bit of thinking to do before we can address that. Obviously, erosion requires a couple of things. It requires an atmosphere. And that's because without an atmosphere, not only can you obviously not have wind, but water depends upon an atmosphere as well. Ice is a little bit tricky. You could in theory have, well, okay, requires an atmosphere except for ice. Ice can be found in outer space and on the surfaces of some planets, and it can cause many forms of erosion. Also, the rotation of a planet helps. One thing that's interesting about Earth, sorry, oh, I'm doing the wrong thing here. I'm pushing funky buttons. If we look at the atmosphere of Earth, Earth's atmosphere is split up into a number of different cells. So I don't have time to get into the complete nitty-gritty of how wind patterns work on Earth. But if you look at routes that ancient mariners had to use to travel across the sea, even modern day sailors know about these as well. There are sort of global wind patterns that we find across the Earth. I believe they're the trade winds, which blow across the equator, these sort of temperate zone winds that are at mid-latitudes, and then there are these polar wind directions as well. You're here at a mid-latitude. You might have noticed if you watch the Weather Channel that cloud formations seem to move from the west to the east, if you watch the projections of how storm systems move across the US. Now, the reality is more complicated. Sometimes we can get winds driving up from the north and sometimes from the south. But for the most part, cloud structures tend to move across Earth at mid-latitudes from the west to the east. And there's an interesting reason why. Part of it has to do with convection. On a planet like Venus or Earth, rays of light from the sun are more direct at the equator than they are at more northern latitudes. And as sunlight strikes directly over the equator, it tends to cause wide bubbles of air to rise up and cool bubbles to sink in a sort of giant convection cell. But unlike the way this works on Venus, on Earth, our rotation creates a sort of twisting force called the Coriolis effect. Don't have time to get into it right now, but the Coriolis effect is something that happens in a rotating coordinate system, like a merry-go-round. It actually causes the motion of objects to twist and bend, in the case of Earth, to the right. This tends to split up Earth's circulation patterns into a set of something called triple Hadley cells. They're like little convection cells, or they're big convection cells in Earth's hemisphere that break up the temperature zones on Earth. They also lead to interesting types of wind patterns. One of the things that I saw when I moved out west for college, something I had never seen before, was a dirt devil. And this is a wind storm. I saw these when I took the shuttle bus from Phoenix to Arizona when I was a college student. I had never seen anything like this coming from Rhode Island. I got off the bus, or I got off the plane, and I was driving in a shuttle bus from Phoenix, Arizona to Tucson, Arizona. And I saw a picture, I saw out the window something that looked exactly like this. I saw this crazy little funnel. It looked like a mini tornado of dirt just whipping across the desert. And there was an old cowboy. He was sitting in the shuttle bus with me riding down to Tucson. And I said to this guy, "Is that a tornado?" And he said, "That there, son, is a dirt devil." And I said, "Well, what the hell is a dirt devil? I've never seen that before." He's like, "I'll tell you what, son, I wouldn't want to get caught in that thing. It'll take the skin off your face. It'll take the paint off your car. These things are little micro tunnels of wind and dust that blow across the deserts, and the grit from these things can just tear the paint right off your car." Powerful form of wind erosion. Any of our service members who've spent time in Iraq or Afghanistan know all about these dust storms. They can get so bad that you have to shut down operations and you're not even able to move about because you can't see in them.
Have you seen the video of the wind that took away the portal potty and flew it across the?
No. Is it pretty good?
Yeah, it's pretty good.
Is it short and worth of watch?
Yeah. Oh yeah.
What do I type?
Just do wind takes portal potty. Yeah.
Will you recognize it if I see it here?
Yeah. I saw it when you were looking up the wind erosion thing. Like they put it.
Is this
There
it?
Yeah, this is
wow.
in Colorado. Yeah.
Whoa. Woo. Yeah,
It gets super windy there.
People forget about how powerful wind erosion is. Whoa! Oh man, that's a mess. Oh no, look at that. That's terrible. I don't even want to think about what that thing is spraying. Oh, thank you, Brandon, for sharing that wonderful video. I'll definitely be using that in the future. I had not seen it. That's amazing.
Yeah, that was in Colorado. It's pretty great.
Let me return the favor by showing you one. These are two images of Mars taken a few months apart in 2001 by the Hubble Space Telescope. In the left image taken on, oh, I'm not sharing my screen with you. I'm sorry. Let's try that again. In the left image, taken in June of 2001, Mars is showing clear skies, and you can clearly see the ice caps, as well as interesting surface features like the volcanoes of Mars and the Valles Marineris. Here are the ice caps. Now, a month or so later, you'll notice that instead of seeing all these surface features, the entire atmosphere of Mars is covered in a global planetary-wide dust storm. This is a dust devil that's the size of the entire planet. So Mars actually has global dust storms that blanket the entire surface of the planet at once. And that's weird because we're not used to storms covering all of planet Earth at one shot. They're usually localized. But these storm systems can just blast dust across the surface of Mars. Now, in a few moments, we're going to start our Mars lab, and it's kind of interesting what happens when you look at the surface of Mars. Let's just grab a random picture of the surface of Mars, and I want you to think about how rocks on Mars look different than rocks on Earth. So take a look at these. I don't know if this is a high enough resolution for you to see what's going on here. Let's get a very high resolution image of the surface of Mars, even higher than that. This is 4,000 pixels. That might be what we need. How would you say the rocks on Mars differ from the rocks on Earth if you had to look at them?
They're more jagged and like.
Yeah, why do you think, Brandon, walk through the planetary science. Why are they so jagged? They look like arrowheads or flints or something, right?
Well, I know erosion causes them to become smooth and stuff.
Exactly, but in particular on Earth, we have a lot of water erosion, right?
Yeah.
So the water erosion tends to smooth them out, kind of like pebbles in a brook.
Would that be wind erosion then?
Well,
Or
the pointiness comes from the lack of water, but you can see the effects of wind erosion if you look up close at some of the larger rocks. Now let me see if I can, it's hard to see in this picture, but the surfaces of the rocks are all pitted and grooved with these, it kind of looks like acne scars or something. High resolution surface of Mars. We just got to find a couple of up close images of the Martian rocks. They look all chewed. Yeah, okay. Can you see the surfaces of these rocks? How they've got all those tiny little holes in them?
yeah.
That's the sandblasting there. So that's the wind erosion. So the jaggedness comes from the lack of water, but you can still see erosion in the form of wind and those sandblasted jagged pits that come from tiny little pea-sized grains of sand like projectiles smashing into the rocks. Over time, this can wear down the rocks on the surface of Mars. So Mars actually by the way, the surface pressure of the atmosphere on Mars is hundreds of times less than Earth. So the winds don't carry the same force on Mars that they do on Earth. But on a windy day, you can push some particles that will over time create this type of sandblasting sort of sand erosion. Obviously, erosion depends deeply on atmospheres. And that's why we need to talk about those. I think we're going to have to save that for next time because I've used up all the time I have today, except for our lab, of course.
Maybe. Not sure.
What we're going to do now is we're going to do a Mars lab together. And on our final lecture, we'll try to do a mixture of atmospheres and Jovian planets. We'll do whatever the hell we can. Let's head on over to our lab room.
Oh, which one do I need to print out?
I'll get to that in one sec because I got to print it out myself.
Okay.
Gesundheit. You got the corona, Zach?
Oh, hey.
Are you sick?
Hello. No, just a cough.
Okay. All right. I want to hear that you're well, my friend. Ever since you went to Florida, we don't see you anymore.
Yeah, I'm just trying to figure some stuff out over here.
All right, buddy. Whatever you got to do. Let's see. Let's see what we got for our Mars lab here. I'm going to want some of these images today, so let's keep that up. Let's keep that up. We could keep that guy up. Get rid of our dirt devils, although I do enjoy those as well. Get rid of our ring of fire. Maybe keep open one heavy bombardment. We might not. We might want some craters. Who knows? Oh, we definitely want that. We do not. We might need this after class, but not right now. Okay. So let's get rid of those. Let's get rid of this and this. And let's go to our attached Mars lab. Actually, I think I'm going to open it up from over here. You are slow. Okay, here we go. Labs. Mars. You want to open up your Mars topographical map. And you also want to open up your landscape of Mars. Brandon, I think we need to print out most of this, unfortunately, because this is going to be a different kind of lab where we answer a whole sequence of questions. So I'm just going to print the whole thing, and I think you should too, okay? We could print it on both sides of the paper. That'll save a little bit. Okay. The printer's starting up. Yeah, unfortunately, Brandon, we need most of it.
I'm gonna go print mine. I'll be back in like 3 minutes.
I'm sorry, I couldn't hear that. Could you say that one more time, my friend?
Yeah, I'm gonna go print mine. I'll be back in like a few minutes.
We can wait for you, Michaela.
Thank you.
Okay.
Before we start the lab, I just had a quick question about last class lab. I kept submitting it, but when like I went to go see, it showed that it was blank.
Yikes.
But you download it, it shows like my writing on it, so I don't know.
What I'm gonna see?
Yeah.
Let's find out, shall we? That's a perfect thing to do while we wait for everyone to print out. I'm sorry, say that again?
Because I uploaded it once and then I tried again and it kept coming out like the same way.
I did not grade your labs yesterday because I got stuck doing, well, not stuck. I was having a wonderful barbecue at my father's house and eating potato salad and burgers. So that may not be a good reason to not grade your papers, but it sure felt like one at the time. I'll get to them before our last class. Let's see what we do have here. Come on. I don't understand. I don't understand why you do this to me. Okay, here we go. Let's see my grading center, what you got. Which lab are you talking about? Do you know the number?
What number is this? 8? So 7?
No, this is like 10, right?
Oh, I don't even know anymore.
Well,
yeah, so lab 9, sorry. The last lab we did.
Hey, Professor.
Yes.
On the last YouTube video, I'm pretty sure that was, you posted the one from like 2 days ago. Like the 2 classes ago.
I think
you were supposed to post the homework 7 and lab 9.
Who am I talking to right now? I'm just having a little confusion.
Zach.
Oh, okay, cool. Zach,
I
so
tried, because the class I missed last class, I'm pretty sure you did the homework 7. On the
okay. All right, let's get to the bottom of that now. Hold on.
Okay, because the last YouTube one you have posted the homework 6 and lab 8.
The last class we had, we did homework 8, lab 9.
Homework 8? So you what?
Yeah,
did you guys
because
skip a
today
homework?
I'm not sure, but today it's like when you go on
I
Black.
thought we did homework 8 today.
Yes.
I might have just written the wrong number on my homework then.
Hold on. Let's figure out what's going on. What was the date of the last class? The date of the last class was the 17th, correct?
Yes.
Yes.
So this is the 17th. I actually had a problem. I have homework 7, lecture 9, lab 9. Are you telling me I did not post this?
Yeah, you didn't post that. It says the last one, the most recent one you have is 5 days ago, and it was homework 6, lab 8.
Oh, bloody hell. I must have gotten distracted. And so this is AS1010. Oh, that sucks. That's on the 16th that I published those. Wow, I was a big slacker. Okay, you know what happens, guys? To render the video, it takes a couple of hours. So obviously, I'm not going to sit in front of my computer for 2 hours and watch the bar slide along, right? I end up going and I do other stuff. But then if I take a bike ride and I'm outside in the sun, and then I come home and I eat dinner, it's real easy to forget to upload it. You know what I mean? Then the weekend hits and I'm like, bah. So it actually, sometimes you guys send me little reminders and that does help. let's start that process now so you can see what that's like. So if I hit create, you can see it's just a little bit annoying. So I'll select the file. Let's get that thing up there. Summer, and that was the 17th. Homework 7, lecture 9, lab 9. So you
So
need
we
this.
skipped lab 7.
Yeah, we skipped the lenses and
Okay.
telescopes because we were talking about the sun that day, and I decided that it would be
Okay.
more.
I was kind of confused on which one
I
missed.
know it's
Yeah, no, it's okay. I got it.
So here you can see the link. This will be the link. Copy link address. Okay. Hit next. Let me get going here on this. Public. You'll notice, Zach, that it's going to take another 43 minutes until this is up. But
okay.
the good news is when it does finish, this will be the link. Let me put it in the chat room. So that will be the link. So when lab is over, you should be able to go and watch that and get her done. Okay?
I have a comment.
Sure,
Can
Megan.
we just see if that lab is, if you can see that lab?
Huh?
Oh, I had asked you if you could see my lab 9, and then everyone
Started going, yeah, buck wild. Okay, so let's do that while we listen to Megan's. What do you think, Megan?
For tomorrow, I have to go to work from 10 to 12.
Do you mean tomorrow or do you mean Wednesday?
Oh, Wednesday. Yeah, Wednesday.
Okay.
So I'm gonna miss the homework thing,
Okay.
but I'll be here for the lecture.
Okay. So you'll just do the homework by watching the video later then, I guess? Does that make sense?
Yeah.
But I'm glad you let me know because I would be worried if I didn't see you on the last day. So
I know.
where are you, Megan? Let me find your face. So I understand, and that's fine. As long as you don't mind watching the video after. Is your message, is your point better get that video up right away, dummy, because it's the last day and I want to make sure that I can do it?
No, I don't care when you upload it. Because when you do, I'll just do it right away. But up to you.
Well, that is motivation for me to think about making sure I don't get distracted. Because as it's our last day, we'll all want to tidy up our affairs probably, right? I don't mind if you get it into me on Thursday or Friday. That's fine too. So just don't forget to remind me because you'll be there for lecture and lab. Remind me to post it right away, okay? Now, this actually helps us because now that we know that we just uploaded homework 7, I'm sorry, was it the lab 9, right?
Yeah.
Hold on, guys. I'm trying to show all the 36 items so I can see. Blackboard is awful. It frequently just thinks and gets stuck thinking. Okay, and Tess, I do have your lab 9, so you should be good. Should we click on it and see what happens?
Yeah.
Yeah.
All right, good.
That's good business, right?
Yes, thank you.
Okay, so while I'm sharing, let's go back to our Mars map here. Can we do this digitally? Can you all call up a PDF showing your Mars topographical map? Should look like this. And I'm going to destroy this pane. This is the Mars MOLA map. This map was made by sending a spacecraft in orbit around Mars that shined a laser down at the surface. And as the laser bounces off of the surface, they measure the reflectivity and calculate the height of the features underneath. So it's basically like a 3-dimensional map of Mars. Now, you guys know from looking at pictures in class that the entire surface of Mars is covered in a uniformly red dirt all over its surface. We can't call it soil because soil implies that there's organic elements in it, but we've not found any organic materials on Mars to date. It seems to be barren of water and of life, more or less, at least as far as we know. Certainly the motivation of some of these rovers is to try to look for ancient fossilized microorganisms and trying to determine if a earlier, wetter Mars might have had some kind of living organisms. But everywhere you go, if you look at the global topography of Mars, the entire planet, as you can see here on Wikipedia, this is a nice 2000 pixel image, is uniformly covered in a sort of red terrain. So the map that we're going to be looking at today is not showing you the true color. The colors, of course, represent different altitudes on the surface. And on this map, by the way, I should have told you guys, we don't even need to print this out. You can type stuff up if you want to. Let's look at our elevation key really quickly. Lowest levels are in purple and blue. Higher levels are yellow, orange, red. Brown will be the tops of volcanoes, and the very tippy tops can even be frosted white. So you can see some of the highest places of elevation are up at the top of these mountains like Olympus Mons. In today's lab, we're going to walk through the questions and sort of answer them as a meditation on the surface of Mars. And you guys will kind of write these things with me here. Start with our first question. Actually, it's the second question. You've probably noticed that the northern hemisphere of Mars is very volcanic, and the southern hemisphere is heavily cratered. Using the concept of crater density from our lecture today, which hemisphere do you think shows the oldest landscape? Would you guys say northern or southern? Students?
That'd be southern, right?
Yes, and why is that?
Because of the craters.
Right. More craters is an older surface.
Yeah.
Okay. At first, the story will seem simple, and it'll get more complicated as it goes. So, Brandon, it now says, inspect the Mars map provided. Locate two basins in the southern hemisphere. The Argyre planitia is near longitude 40 degrees and latitude minus 50 degrees. Hellas planitia is near longitude 290 degrees and latitude negative 42 degrees. These two basins were probably formed by giant impacts of meteorites. Let's just look and see if we can find them right now. Oops. Oh, wow. Excuse me. I'm getting the... Here we go. So you guys, if you can see my screen, notice I've framed the Argyre planitia on the left and the Hellas planitia on the right. What do these resemble? This looks like something we saw in our last lab. What would you guys say this reminds you of? What other geological feature?
The
Yes?
you know what I'm talking about.
Well, but do you know what you're talking about?
Yeah,
That's the real question.
It's the, hold on.
If you don't know the word, you don't know what you're talking about.
No. I got it. 1 second. Where is that goddamn map? It's the Maria.
Very good. Don't these remind you of lunar Maria?
Yes.
So these are some pretty big boy impacts, right? Well, let's just read the rest of the bloody question first. The basins were probably formed by giant impacts of meteoroids. The smooth surfaces at the bottom of these two large craters are lava flows. Using the map, try to determine if you think that the lava flows occurred before or after most of the heavy bombardment in the early solar system? So did the lava flows occur before or after the heavy bombardment that was responsible for these plains?
It'd be after. Most
Yes.
of them.
How do you know that this came after this?
Because the a lot of the crater, if there are craters, are filled in from the lava flow.
Okay, but even one step before that, there just aren't many craters here compared to here,
Yeah.
right? The density of craters is lower inside the basin than in the surrounding highlands. Let's do that. So you're saying they came after, right?
Yep.
I'm sorry for Michaela and all those who are printing out, you probably could have just typed this up if you have Acrobat Reader, huh? That might have been easier for several of you guys than to print it out. I actually printed mine out too, not even thinking about this. You know what's funny? Last night, I didn't do anything bad. I didn't drink, and I got a good night's sleep. And I feel more tired today than I do during a normal class. What the hell is that all about? I have no idea what's going on.
Because you messed up your routine.
Maybe that's it. What were you gonna? Who else had something to say about that?
Megan, I feel the same way.
You think you feel the same way? Yeah. It's like as soon as we do the right thing for once, it ends up working out worse. I have no idea what's going on, but I'm yawning like crazy today, despite having gotten a much more reasonable night of sleep than I normally do when I see you guys. Anyways, the point being, please forgive me, okay?
So can you accept a Word attachment or no?
I can accept a Word attachment.
All right, yeah, because I've never sent you a Word attachment.
Yeah, I like a .doc. That's fine. But Dennis, did you notice that I can actually just edit using Acrobat Reader? And Acrobat Reader is free, so why not? You could do the same thing that I'm doing here if you want.
Yeah, I might do it after because I'm not very good with all this. You know,
Here, Dennis.
shit.
I understand that, but let me help you, okay?
Yeah.
Dennis, do you have a web browser open?
Yeah. Like
type Acrobat Reader. Okay.
Like in like a search bar.
Yep. And then go to Get Acrobat Reader.
Download. Free PDF converter.
Not free PDF converter. Look at where I went. Okay. Do you see? Don't go to the ad. Go to this one. Getadobe.com. Do you see Get Adobe Reader? Do you see that link? Here, I'll just give you the bloody link. Whoops. Sorry. Dennis, in the chat window, I'm sending you the link, okay? Click that link from the chat window.
One sec.
You see that? And I'm talking to everyone, not just Dennis now.
Yeah.
Did you click that? Are you here?
Yeah, I'm trying to, because I have so many windows open just from before, so I'm kind of confusing with my screen and your screen.
Oh, okay.
Is the
do you see right here the button?
1 second. Oh, the chat. I got you. All right. Is it the one 319? All right, gotcha.
I've already have it installed, so it's grayed out for me.
All right, yeah. So I got and then it says download Acrobat Reader.
Yep. Install that puppy while we're talking. I know you're trying to pay attention to me too, but at least you can get going on it, okay? Anyways, you're welcome to use the Microsoft Word one as well, Dennis. I don't really care. I shouldn't have messed with
Yeah.
it. I just thought if we all do it the same way, that could be nice. You know, PDFs look nice in that box. All right, once you have that program opened, just right-click the file and choose Open with Acrobat Reader, okay?
Yeah, let's see if this is select not.
Okay, we have to say why. Why, Brandon, do we know that the basins, the lava flows formed after the heavy bombardment? What is the evidence, the visual evidence that tell us that the basins came after the highlands?
Because it's smooth from lava.
Yeah, pretty much. I'm going to
Okay.
say it this way, and you guys can follow my moves, but that's fine. I'm going to say that the density of craters in the basin is much lower than the crater density. Let me minimize myself. In the surrounding highlands. I guess I should. This is nice because it uses a couple of our key terms. It uses the term basin. Can I underline? That would be kind of cute. Well, whatever. It uses the term highlands. How you doing, Dennis?
I'm working on it. I just have to pop it up.
You right-click the file and choose Open with Acrobat Reader.
All right.
If you wanted to use Microsoft Word, that's fine too, but I think this is better.
I might just do that. I might just do that for today, just so I can keep
Just
following along with you.
Dude, I can read I shouldn't have met, you know, I can totally read a document file as well, okay? I guess I was worried that it might have formatted it weird, because sometimes when you open up Reader in a document form, it gets funny.
If it does, you can just email me and I'll be able to do the Acrobat.
Okay.
Do it quickly.
It'll probably be okay. It'll probably be okay.
All right.
So let you catch up to us here.
No, I'm caught up now.
Oh, good, good.
All right.
Is everyone ready to go forward? So I got a question for you guys. Are these big or are these small impact craters that created the planetias? What do you think, Ian? Is this a big impact site or a small impact site?
I would say big.
Yeah, I wonder how big is it? How do we do this? Let's see if I can annotate. It's about this big, right? Let's see if I can move that. Oh, shoot. Let's undo that again. Let's try to draw this really horizontal. Okay. I want to show y'all something, okay? The way this works is you can move. What latitude do you guys think this is? What latitude is this here on the map? The center of that puppy is like, let's see here. That's negative 30 degrees. That's negative 50 degrees. So what would you guys say is the latitude here? Can you guys help me read that scale?
So what's negative 30 and what's negative 60? I wasn't looking at the screen for a second.
This line is minus 30 and this line is minus 50. 30, 35, 40, 45, 50. What's the closest latitude?
Is it negative 43?
Yeah. Now, when you measure a distance on a globe, the globe is a three-dimensional surface that's been flattened into a two-dimensional surface. We have to use these Mercator projections down here, and we want to slide this under, shoot. Basically, I just want to know how many kilometers across is this thing. Let me see if I can select it. So I'm going to move it down to minus 40. And what would you say about how long is that line on the Mercator projection? Just roughly speaking.
1,500?
Totally effing not. Look, these lines of constant latitude, they travel along these Mercator projections here. This is 2,000 kilometers, but it's different at the equator than it is at the North Pole. We're at negative 40, so that's the start, that's 0. And Brandon, you can see it going out to here, which corresponds to roughly how much at the minus 40 Decatur? Or Mercator, I should say.
2,100?
Yeah, something like that. This is over 2,000 kilometers across, right? So that's, how big do you think the meteoroid that struck it was?
Huge. Massive.
I'm asking about size. Give me a number. What's the rule of thumb for the size of the impact compared to the size of the impactor?
Isn't it 10 to 100 times?
Sure. So if this is maybe like 2,000 kilometers, I ask you again, Brandon, how big do you think the thing was that hit this thing?
20 kilometers maybe? No.
Or 200 even, right?
Or 200,
Somewhere
yeah.
between 20 and 200. Is that your everyday sort of impact, or is that your bigger than average impact?
Bigger than average?
How often would you expect something like that to hit?
Every 100 million years or once in Mars history.
Except there's not one of them, but there's two of them, isn't there?
Yeah.
So let's say the thing was maybe 20 kilometers or so. Maybe it would hit once every few 100 million years, right? But heavy bombardment only lasted for like 1 billion years. So I'm just having a hard time understanding this, Brandon, because at first I had a very easy, simple story to tell you. And the story was, let me find my doodad here. At first the story was, at one point there was a lot of heavy bombardment. And then after that, there's some lava flows in these basins. But the story is also that these big objects struck the surface of Mars, and these aren't the kind of things that would strike all the time. In fact, I would expect that something of this size would have only been able to strike Mars during heavy bombardment. So I've got one of two scenarios, Brandon. One scenario is heavy bombardment was going on, splat, 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 splat. And at the end of heavy bombardment, when all the splatting was over, then I got two really big splats. One massive, one giant one for Hellas and one giant one for Aguirre. Another possibility is that these giant objects occurred, we wouldn't expect them to occur right next to each other. They'd have to be separated by at least a few 100 million years, maybe even 1 billion years. But if they happened during heavy bombardment, why aren't their basins more heavily cratered like the highlands? Do you understand the conundrum?
Yeah,
All right.
kind of. Does that mean that it would have had to have been before heavy bombardment then?
Well, heavy bombardment is like the first 1 billion years of the solar system's history. I would have expected that if some really obnoxiously big meteoroids were going to strike, I would expect them to strike during heavy bombardment. And I wouldn't expect them both to happen on the same day. I wouldn't expect them both to happen afterwards. I'd expect one to happen in the middle beginning and one to happen in the middle end. You know what I mean?
Yeah.
But the surfaces are smooth as if they happened afterwards. You know, sometimes the rim of a crater can tell you about its history too. I'd like you guys to look at two craters with me. In one case, I'd like you to look at crater Huygens, and I'd like you to check out its rim, and then I'd like you to look at the crater Dawes. Can you tell me which is older, Huygens or Dawes, just by looking at it?
Huygens.
How do you know?
Because it's spidering out.
Say that again?
Is it because it's it has the rays?
Well, okay. All right, it kind of has some rays. I'm not going to say it doesn't, but there's something else that tells me that this is older than Dawes. It's got something to do with the rim of the crater.
Is it lower?
They look about the same altitude. They're both kind of pinkish orange.
It looks a little more like layered a little bit, like kind of like it's like over time, like kind of like eroded a little bit. I don't know.
Yeah, not only eroded, but look, Dennis, the rim is actually also being struck by impact craters, right? But it also does look like erosion has worn down on this. I think this rim is a little bit sharper and crispier. This has been beat up over time, you can tell. Sometimes the basins can look the same, but the rims can tell you a very different story. All right, let's read the next question. Use the map and inspect the rim of Aguirre Planitia and Hellas Planitia. Look to see if the rims have more craters than the lava flows inside them. Look for evidence of ghost craters, which have been filled with lava. I think by ghost craters, they mean like, I don't know, like maybe that thing there, or maybe like that thing there, or maybe like these guys. So based on the rims, which following historical account seems most likely? A, the giant impacts occurred early when most of the other impacts occurred and excavated the basins with their surrounding rims. The lava filled the basins much later after most of the heavy bombardment was over. B, the giant impacts just happened to occur very late after most of the other craters had formed, and the lava filled the basins immediately after their formation. What do you guys think, A or B? Work with me. Talk to me.
Would it be B?
What evidence would back that up?
The lava filled it immediately.
Okay, what about the rims? How the rims looking?
Oof. Looks like it. Honestly, I don't know.
What does this remind you of? What type of geology caused this?
Volcanism?
No, no. Look, volcanism, this is what volcanism does. Do those rims look anything like this smooth plane?
No.
Hell no.
Erosion?
Yeah, these remind me of like the sort of sand dunes, like aerial pictures of sand dunes. I bet water washed all this thing out. Also, the rim has been beat to shit by impacts. Look at Gale Crater, where currently the Curiosity rover is driving around looking for evidence of life. This thing has been beat all up. The rim has. The thing I'm having a hard trouble understanding, Brandon, is if the impacts occurred both at the same time, late after heavy bombardment, why are the rims showing evidence of heavy bombardment and erosion? You see what I'm saying?
Yeah.
I think we want to go the other way. I think we want to, oh shoot. How does this work? I think we want to circle A. What evidence helps us make this decision? What's the evidence?
Would it be the outside of the craters and erosion?
The rims show evidence of impacts, cratering, and erosion, suggesting they are old.
Wait, was that right? I was just totally guessing that.
Yeah.
Oh, okay. Like, well, I kind of understood it, but I didn't know if that what I said was the correct way of saying it.
Yeah. The difference between you and me is I focused on tangible things, the rim. I'm focusing on the rim, and that's a vocabulary word that I have, which will help me explain what I'm talking about. I need to say that there's some piece of evidence suggesting these things are older than they look, and mine is the rim. They show evidence of cratering and erosion. The theory in the moon, how the moon goes, is the impacts occurred during heavy bombardment, but that radioactivity and thermal heating from the interior of the planet helped melt and form these vents that eventually filled up later, after millions of years, filled up with pools of lava. Look carefully at the crater density along the rim of Hellas and Aguirre. The basin that's older should have more craters on top than the younger one. Does Hellas or Aguirre basin look older?
Hellas.
I don't know. I think the Aguirre looks older just because you can see more impacts and more erosion of its rim. This rim is still relatively oval and intact. I think that's the best science that we have on record, too. I believe the consensus is that Aguirre Planeti is older. Let's fact check that because I've been known to get a few things wrong. The basin was probably formed by a giant impact approximately 3.9 billion years ago. And let's compare it to the Hellas planitia. Oh, wow. That's a little bit confusing, huh?
What was the other one for billions of years?
I think you were right, Brandon.
Yeah.
Well, it's a little confusing because this says 3.9 and the other one is 4.1 to 3.8, right?
Yeah.
So there's some uncertainty in the research. So let's just make some good evidence. Brandon, what makes you think Hellas is older? Sorry.
Well, because it had more time to get filled in by lava and everything. And
when it's filled in, that means it's younger, right? Like if you repave your driveway, it's now a younger surface than the old driveway.
yeah.
Do you see what I mean?
Well, could it be smooth from wind erosion?
That also means it's a younger surface. I guess if you wanted to argue Hellas, you could argue, well, I see some craters here in the basin, right?
Mm-hmm.
But if you look over here,
Which those would technically be newer ones, the ones in the middle.
you do see, yeah, you do see some impact cratering. This is a tough one. I'm going to give it to you. Although I normally say Aguirre is older, I'm gonna let you say it because it seems to be some uncertainty in the results there. They say the basin that's older should have more craters. The basin that's older should have more craters on top of its rim. You know what? Based on that, if it's based on the rim, which rim shows more craters? Hellas or Aguirre?
Maybe Hellas. Well, maybe.
It's confusing, right?
Yeah, because I mean, it's kind of almost this. By just looking, it's almost the same, kind of. I mean, we'd have to actually count every single one, and I don't think we're gonna do that.
Yeah. No. We have to do it by. Although a hardcore planetary scientist might, to make sure they were being objective. I'm gonna let you go with. I always believed that the Aguirre planitia was older, and I thought I had looked it up a long time ago, but maybe the research has since changed. Hellas planitia was formed during late heavy bombardment, anywhere from 4.1 to 3.8 billion years ago, whereas the Aguirre planitia, late heavy bombardment, 3.9. So it sounds like people aren't really sure. The scientists have some uncertainty about it as well.
That's wonderful.
Why don't we go with, let's go with your answer, Brandon. I like it, okay? We'll say this time Hellas planitia. And I think your argument for why was the basin and the rims show a higher density of impact craters compared to Aguirre. Okay. Everyone got that?
Hold on.
Let me get some iced tea. Hold on. Some coffee or something. I don't know if you guys get coronavirus paranoia, but every time I feel sleepy, that's one of the symptoms that people have sometimes when they first come down with the coronavirus. I start like going crazy and wondering, maybe I'm really tired because I've got the bug, you know? I don't know. But normally I don't feel this tired when I'm teaching the class. So let's knock on glass here. You too, Megan, right?
I have a sleeping disorder, so no corona for me.
Oh, okay. All right. Well, that's a legitimate reason, I guess. Hey, let's read the next one together. Most of the volcanoes on Mars look like mountains with a crater on their tops. These are not impact craters, but are instead volcanic craters. Boo! We don't like that talk. What's the word that we use here? What's the vocabulary word that you learned today for volcanic craters?
Impact craters?
No, for the volcanoes, for the tops of the volcanoes. Consult your diagram.
Oh, yeah.
Calderas?
Thank you. Okay, that's better. Most of the volcanoes on Mars look like mountains with a crater on their tops. These are not impact craters, but instead are calderas. Use Google Mars to estimate how many volcanoes you can identify on Mars. Oh my, damn it. Okay, this is a tough one. Let's go over here. And I want to show you guys what volcanoes look like from a topographical sense. Anything that is a mons is a volcano. We got these four big boys: Olympus Mons, Ascraeus Mons, Pavonis Mons, and Arcea Mons. But these things called pteras are also ancient volcanoes, and so are the tholuses. So let's try to clear, and let's see if we can keep track of them all. 1, 2, 3, 4, 5, 6, 7, 8.
Did you say Tholuses are one?
Yep. Tholus, Patera, are Mons. So I've got 8 so far. 9, 10, 11, 12, 13, 'Let me know if you see any. 13, we got more hidden over here. Oop. 14.
What are dorses?
Where do you see that?
In the Solus Planum, there's a Solus dorsa.
Bear with me here. I don't know, but I want to know. Maybe I can learn something today. I'm having troubles. Is that where I am, or is that where you are?
Oh, sorry, hold on. I was looking at my own map. 1 second. Okay.
That's cool. That's cool. Wait, hold on. What number was this one again? I'm losing track. Was that 14? Thank you, Michaela. Let me answer that question in 1 second. I'm going to get distracted here. 14, there's 15. 16, 17, 18. Let's look at the South Pole. I think there's some up there. Oh yeah, 19. The more you look, the more you find.
There's 20.
Yeah, about 20 or so. Let's just go with that just to keep things simple. We will say tilde 20 for approximately. Hey, why doesn't tilde work? Huh. Some reason that you know what I mean by tilde, right? It's like a squiggly. It's approximately 20. Okay. Let's not list the names of as many of the volcanoes as possible. Let's list the 4 big boys, okay? The 4 big boys include Olympus Mons, Escraeus Mons, Pavonis Mons, and Arcea Mons. Did I spell that right?
You were on the area that I looked up that Dorsa thing.
Oh yeah, I want to answer that question because I suspect the answer to that's going to be very interesting. Pavonis Mons, Arcea Mons. Let's let everyone, including yourself, Brandon, get those answers. And then I want to try to answer that question. And it's called the Dorsa?
Yeah, it's in the well, when you pull up the map, I'll show you. I know where it is.
Okay.
Okay.
Tell me where to go. Up, down, left,
so,
right?
Go down. You see where it says Solus Planum?
Yes.
Okay, so it's to the right of that. You see where it says Solus Dorsa? But there's multiple of them too, so I don't know what those are.
There's some kind of geological feature. I'm going to try to guess what I think they are. And then let's see how close I am at guessing, okay? I like to play this game. I believe the Dorsas are these crinkly surfaces, which I'm guessing are tectonic in origin. I bet it's where volcanic flows freeze and kind of make these ridges or lumps. That's my best guess. Let's see if I'm anywhere a Dorsa. And we might have to type Dorsa geology. Are you looking it up?
Yeah, it said, I looked at Solus Dorsa and it's, Wikipedia said wrinkle ridge, an instance of a wrinkle ridge.
All right, so I was right, but does it tell you it's from frozen volcanoes or from tectonics or something? What?
Let me.
Wrinkle ridge, huh?
Yeah.
Which is pretty much what I said.
Says wrinkle ridge is a type of feature commonly found on lunar maria. These features are low, continuous ridges formed on the Mars surface that can extend up to several hundred kilometers. Wrinkles ridges are tectonic features created.
So that would mean, you know those earlier pictures I showed you of the frozen volcanic lava on the moon?
Yeah.
I think that would mean that, let me see if I can find the actual place here. Remember I showed you, come on, baby. Give me the preview. When I was showing you the different types of volcanism, I was showing you, where is it here? Slide 60. That would make these Dorsas, wouldn't it?
Yeah.
That's nice. You helped teach me something new today, Brandon, and for that I am grateful. These are Dorsa structures. I always call them, they look to me like pancake batter. By the way, a picture I didn't show you today that I felt kind of bad about, I was stressed about time. This is what basaltic lava looks like when it's frozen. Can you guys see the differences between these two types of lava? This is very low viscosity lava that can flow for many, many hundreds of kilometers before cooling down. Other types of lava are kind of thick and viscous. this type of lava would form stratovolcanoes, where the runnier lava would either form shield volcanoes or even volcanic plains. And when they freeze out, that's probably when they become dorses. So that's kind of interesting for the following reason, Brandon. That means you can literally see the flow of lava from those volcanoes freezing out on the surface of Mars, right?
Yeah.
Like it looks like the lava was actually flowing like in that direction, right? Downhill away from the volcanoes. Very cool. Very cool point. All right. Now that we've got that, I think there's a real softball coming our way here. Using the elevation. I'm sorry?
Can you show the answer for number 7 again? I
Sure.
just wrote it down.
Just the 4 big volcanoes.
Thank you.
Okay.
Oh, we're not even halfway done with this lab.
Huh? Oh, we're gonna be done before you know it. I'll try to speed up. Let me check the time. Oh my God, I'm doing bad here today.
No, I just need the last 2 on the 4 volcanoes.
Sure.
Mons.
Were you noting, Brandon, that it's almost 4 o'clock? Is that what your point was?
Yeah. Yeah. That's why I was like,
And we didn't get number 6, right?
Yeah, we got tilde 20, right?
All right, cool.
I don't know why I'm going so slow today. What's wrong with me? Oh, actually, maybe you guys are contributing to that too, because sometimes I ask questions and it takes you a long time to answer. So we all suffer for that kind of stuff. What do you think is the tallest volcanic feature on Mars?
that'd be Olympus Mons.
Easy peasy.
Yeah.
Now, this question I used to find very difficult. If you were to count craters on or near these volcanoes, would you be able to infer the age of the volcanoes relative to the surrounding plains? To answer this question, it would be helpful for us to look at an up-close and personal image of Olympus Mons. So let me get out of this here. And first of all, let me go back to this sheet. And I want you guys to notice that, can you see those 2 little dots up there at the top of Olympus Mons? I think they're referring to these little blips that you can see. But luckily there's a high resolution image of Olympus Mons that will help us here. It's this one. Now, what's going on up here? Let's play a quick game called Crater versus Caldera. In this picture, what is a crater and what is a caldera? Let's start with the main opening. What is it?
The main opening's a caldera.
Good. How about this guy?
Crater.
Caldera. How about this guy?
Crater.
Caldera.
What?
How about this guy?
Caldera.
Crater.
Yeah.
How about this guy, Brandon?
That's a crater.
Very good. Now you get it. Can you see how the calderas have these kind of sloping edges to them?
Yeah.
The craters are a bit crispier. Brandon, what does it mean if I count not 1 but 2 craters at the top of Mars's tallest volcano? What's the implication?
That it was before the heavy bombardment period?
Oh, hell fucking no. Look, man. heavy bombardment pockmarks the surface. Look.
That the volcano's old.
How old?
Older than those craters.
Okay. Look at the surrounding plains. Do you see how smooth it is? In general, this is a quite young geological surface, except for those 2 pesky craters. What if I told you that these are thought to be the origin of the Shergatti meteorites on Earth? I believe this one is about 15 kilometers in diameter. That one is about 10 kilometers in diameter. Keep in mind that meteor crater is 2 kilometers in diameter on Earth.
So
How
that's-
often, what size impact would have made these if it's 10 and 15 kilometers?
That'd be 150 meters, right?
Just do it in kilometers. Oh, okay, fine. All right. No, you're right. You're right. Okay. 150 meters, you're saying, right?
Yeah.
Like 1 kilometer or so, right?
Yeah.
How often would that strike Mars in general?
Every million years.
Yeah, somewhere between 1 million to 100 million years. So how long has it been since Mars erupted? I mean, sorry, since Olympus Mons erupted?
100 million years.
Yeah, maybe something like that. Let's look it up.
$115. There it is.
You did pretty good, didn't you? So the message of that story goes something like this. Well, what's the answer to the question?
Yes.
Yes. And we will say, I'm sorry, I don't want to be using this. I want to be using this type here. Nope. Sorry. Nope. Let me get rid of this. I want this type here. Yes. Even 1 or 2 impact craters is enough to determine a rough, wow, age of the volcano. Something like that, right? Tharsis bulge and Valles Marineris are thought to be caused by internal magma intrusions deep inside Mars. Inspect the area of the Valles Marineris between 45 degrees and 100 degrees. Notice that the area is not uniformly cratered or wrinkled. A boundary seems to occur at what longitude? So let's go over and let's take a peek at the Valles Marineris. They're talking about this region here, from 45 degrees to 100 degrees. Now, if you look at the scale or the chart, we have 30 degrees here, 60 and 90. So this is the 30, 60th, and 90th longitude line. So 100 degrees would be like here. And 45, 60, 55, 50, 45. Do you see a boundary south of the canyon? Somewhere in this box, do you see a boundary between 2 planes of different ages? What's the boundary that they're talking about?
The chasm.
The chasm is not it. They're talking about a vertical boundary. Because they ask at what longitude. Longitudes run like this, right?
Would it be the Nectaris fossea?
That's right. And approximately what longitude would you say that occurs at? These are each a degree.
What was the starting degree again?
What do you mean by starting degree?
Like with the boundary on the left, your first red line on the very left.
Well, that's what I'm, oh, this is 100 degrees. Here, let me help. This is 90 degrees. This is 60 degrees. This is 30 degrees. It's 1 degree per tick.
58 degrees.
Yeah, I'd say it's pretty good. Is the younger surface to the east or west of this boundary? This direction is west. This direction is east. Is that right? Do I have that right? Yeah, west is increasing to the left.
It'd be to the east.
Wait, you're saying that this is the younger area?
No. Opposite way around. Yeah, that
To
way.
the west, right?
Yeah.
Okay. Look at the smooth region named Tharsis Montes. Does the crater density suggest that Tharsis Montes is older, younger, or the same age as the region south of the Valles Marineris? So is this stuff younger or older than this stuff? Actually, they're asking about Tharsis Montes. They want to know, is this area here younger or older than this stuff over here?
Older.
How do you figure?
Because it's all smoothed out. Because well, then that would make it newer.
Yeah. Right? Well, you fixed yourself. It's crater density determines how old you are, right?
Yeah.
Do you agree, Brandon, that there's more craters there than there are here?
Yep.
So the Tharsis Montes is much younger, which is the answer to that question.
I don't know why I keep sticking to like lava flow would technically fill in craters, and I'm thinking that there could be craters underneath there, and that's my
Right. Well, the problem is, Brandon, that all the planets are old. They're all 5 billion years old. But the layers that keep reforming them get newer and newer, right?
Yeah, that's yeah.
That's the
right.
conundrum, and you have to go through this. The surface age is not the same as the planet age. Of course, there are deeper levels that are older underneath. But if we're talking about, we're just trying to say, are the surface features newer or older? So they're younger. Okay, question 13 is really cool. Along the north rim of Valles Marineris is a place called the Candor Chasma Rim. It's located in the canyon regions of Mars and is near 70 and 75 degrees longitude. Does this area suggest that the canyon is older or younger than the plains to the north and south? So they're talking about this region right here, and the canyons in here. And to really appreciate this, I want to show you this super high resolution image. It's pretty wonderful, of the Candor Chasma Rim. They have a very, very high resolution image on Google.
Nice.
Wait. This is the picture, but yeah, 9,000 pixels. Give me all you got. Okay, so look at this crazy image here. You can zoom in so far. It's so cool. So what's going on here? Let's look at this. So here's the canyon itself, right? Let me just zoom out one more click. Oops. Come on, baby. Is the canyon an old or a young geological feature? This is the canyon. Yeah, how do you know that this is way younger than up here and over here?
Honestly, I was basing it off of that one crater right between those two red lines.
Which red lines?
No, go down. Yep, down and down. You said crater that's right on the edge, on the rim?
Oh. Yeah, what about it? That's interesting.
It's broken off.
Yeah, telling you that this all happened way after. The Valles Marineris is one of the youngest features. more to your point, Brandon, look at this area here. There's like hardly a single crater inside this thing, right?
Yep.
Like it's hard to imagine that all the craters went splat, 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 and then just missed the inside of this, right?
Yep.
So what type of geology created this stuff then? What type of geology is responsible for this?
Erosion.
Totally. What type of erosion?
Ice. Glacial erosion.
I don't know, man. This looks like liquid water flowed on its surface. Look at all these. Don't these remind you of sand dunes and dried up riverbeds?
Yeah.
I think these things are called alluvial fans. When water flows across a surface, they create these shapes sometimes called alluvial fans. You might have seen them in aerial photographs before. See this kind of a thing here? Alluvial fan, see that?
Oh shit! I used to see those all the time in Colorado. Yeah.
Oh, did you live in Colorado?
Yeah, 20 years.
Oh, wow. That's super cool. So, so yeah, you really get some cool geology out there in the West because, you know, there isn't as much vegetation to block it all. So,
Yeah.
So doesn't that kind of remind you a little bit of that? So that looks like liquid water to me.
Yeah.
So let's go and answer our question with those things in mind. So we'd say the canyon is younger. Is there anything along the north or south rim that shows evidence of flowing water? Duh. Alluvial fans and sand dunes. I don't know. Well, just leave alluvial fans.
Professor, I have to leave. Can I watch the video and finish it up later?
Okay, I'll tell you what. There was only a couple more questions anyways, and we're getting a little bit late in the day. I'll tell you what. Why don't we just call it there? Does that sound good to everyone? And I'll let you skip the end question so Michaela doesn't have to go back for 2 questions. You guys cool with that?
Yep.
All right. There were a couple of other interesting questions, but you get the idea. Just turn that in, okay, Michaela? In the future, for our last class, I know sometimes you guys might not know the answer to things, but keeping that dialogue going back and forth helps to lubricate the day a little bit. I know that can depend upon the clarity of my questions too, but we only have one more class and then you'll be able to be free of me forever. So turn in those labs, turn in those homeworks. I'll try to get the video posted soon, and I'll see you guys for our final lecture on Wednesday. Sound like a deal? Over and out.